Yeah.
Is this screen visible to all of you?
Yeah.
Yes.
Okay.
Yes.
Yeah.
Yes, Dr. Khan. It's visible.
Visible to all of you? Okay.
Yes.
Good. Okay, thank you. Uh, may I request to all the dignitaries to switch to mute your microphone, please? May I request to all? Yes, please. Thank you, sir. Thank you very much.
It is not audible.
Yeah. Please check. We are not able to hear you.
Not audible.
Dr. Khan, we are not audible. So is anything going on? Is anything going on? I'm not audible.
No, no, no. We are waiting. We are waiting, sir.
Acha. I think something is there. Even our talk is very much delayed.
We are waiting, sir. Timur is not connected.
I guess Dr. Toimur is connected from multiple devices, and that might create some echo.
Maybe, but question is now he is not connected at all.
He will join again. He's disconnected. He will join again.
Hello. Am I audible too?
Yes.
Yes. Sorry.
Hello.
Yes,
Am I audible to all of you?
Yes.
Yes, we can hear you.
Yes.
इससे कोई वो नहीं है क्या करूं what to do now आवाज नहीं आ रहा है भाई क्या करना चाहिए सर
हाँ जी, स्टार्ट कीजिए. अभी ठीक है.
hello everyone
Yes.
am I audible
Yes.
am I audible
Yes, Timur.
Yes, start.
Audible.
Timur,
Yes.
start the program.
Please continue.
YouTube का साउंड बंद करूं ओके
You close YouTube, sir. I mean,
close okay hello am I no am I audible
yes, sir, you're right.
Yes, Timur.
am I audible please
Yes, Timur. Yes.
Yes, you are.
नहीं आ रहा ना कुछ भी Okay.
ये वाला जो है ना वो जनरेट कहाँ से
क्या
ये पीपीटी में मेरे सिस्टम पे करता है मैं आपको वहाँ से एक्सेस दे दूँ
नहीं होगा ना वैसे। चलो ठीक है।
मेरे रूम में उसी में
अच्छा चलो।
आपको क्या सुनाई नहीं दे रहा है ना आओ मेरे रूम में बैठो मेरे रूम में सो
Carry on, sir.
No, I'm not able to hear them.
yeah
I'm not able to hear them. Na?
Dr. Taimur, we can hear you. We can hear you. I can hear you. You may please start.
Yes.
Hello, we can hear.
Okay, sir. Thank you, sir. I am extremely sorry for this network interruption. Okay, sir. Thank you. I am extremely sorry for this network interruption. Okay, sir. Thank you.
Sir, there is lot of echo. Sir, there is lot of echo.
Lot of
Echo.
echo. वो तो ठीक है बट इको Is the echo problem is still existing?
Yes, there is some echo coming.
You can continue. Yeah.
Most of the people should
Yeah.
mute their,
If you continue.
rest of the
Okay.
people should mute their phone and
Yes, please. All the invited dignitaries, please mute your microphone, please. Please mute your microphone, please. I think now there is no echo.
no echo now.
Okay, thank you everyone. Now, I'm first of all extremely sorry for this internet interruption. Let me start it again quickly. Good evening, everyone. As the world is going through global pandemic situation due to COVID-19, routine life of every profession is getting affected in one or the other way, including the students and researchers. However, we believe that learning and knowledge exchange, even in these tough times, should not stop. With the use of technology and online platforms, it has become much easier for all of us to connect globally. So with the immense pleasure and gratitude, myself, Dr. Taimur Khan, convener of this workshop, welcome you all on the behalf of organizing committee of 1 week Indo-Canada SPARC workshop on RF energy harvesting systems, REHS 2020, virtually organized by National Institute of Technology Silchar, Delhi Technological University, Delhi, and Queen's University, Canada, and hosted by Department of Electronics and Communication Engineering, National Institute of Technology Silchar. The workshop is fully sponsored by Ministry of Human Resource Development, Government of India, under Scheme for Promotion of Academic and Research Collaboration, SPARC. Ministry of HRD, Government of India launched this SPARC scheme on 25th October 2018 under the leadership of Shri Prakash Javadekar, Honorable Minister of HRD, Government of India. Basically, SPARC aims at improving the research ecosystem of India's higher educational institutions by facilitating academic and research collaboration between Indian institutions and the best institution in the world from 28 selected nations in certain areas that are at the cutting edge of science or with direct social relevance to the mankind, especially of India. REHS 2020 is a week-long workshop on radio frequency energy harvesting. The aim of this workshop is to provide a common platform to the researchers working in the emerging area of RF energy harvesting and allied domains for delivering talks in their specialized research topics. The course structure of this workshop is designed in such a way that the students, research scholars, faculty members, and industry professionals will get an exposure to familiarize themselves towards the recent developments pertaining to energy harvesting system. At the same time, it will include in-depth discussion on various design challenges that are encountered in this emerging research area and their possible solutions. The workshop will provide not only the essential knowledge, but also a platform to the participants for exchanging their ideas and information with the distinguished invited speakers. Now, on the behalf of organizing committee, I would take the opportunity to welcome our respected director, Professor Shivaji Bandyopadhyay, Dean Research and Consultancy, Professor M. Ali Ahmad, Institute Coordinator, SPARC, Professor Upendra Kumar, Chairperson of this workshop, Professor K.L. Vaishnav, and all other invited guests, including colleagues and my friends. Thank you all for your gracious presence. Next, I would like to pass my warm welcome to the entire SPARC team involved, especially Professor Yahya Antal as Foreign PI and Professor Alpi Frondorfer as Foreign Co-PI, both belonging to Queen's University, Kingston, Canada. Professor Ashok De as an Indian Co-PI belonging to Delhi Technological University, Delhi, India. And lastly, myself, Dr. Taimur Khan as Indian PI from National Institute of Technology, Silchar, who have agreed to jointly organize this workshop using virtual platform as a part of our ongoing SPARC project. Next, my sincere gratitude to all the distinguished invited speakers from India and abroad, especially Professor A. Alphonse from Nanyang Technological University, Singapore, Dr. Nashimuddin, scientist from Institute for Infocom Research, Singapore, Professor M.S. Hashmi from Nazarbayev University, Kazakhstan, Professor M. Palandoken from Izmir Katip Kalebi University, Turkey, Professor K.J. Vinoy from ISC Bangalore, India, Professor Ashok De from DTU Delhi, India, Professor B.K. Kanojia from JNU Delhi, B.K. Kanojia from JNU Delhi, India, Professor J.Y. Siddiqui from IRP Calcutta, India, Professor Chinmoy Shah from IIST Thiruvananthapuram, India, Dr. Brinda Bhaumik, Dr. T.R. Lenka, Dr. Kaushik Gua, Dr. S.K. Tripathi, and myself, Dr. Taimur Khan, all belonging to NIT Silchar, India. Thank you all for your accepting our invitation and agreed to share your knowledge with the young participant in their respective areas of expertise. Next, my warm welcome to all the members of the organizing committee associated with REHS 2020, especially Dr. Ujjwal Chakravarti, Dr. Gaurav Singh Baghel, Dr. Devendra Singh Gurjar, and Dr. Naresh Babu for their keen interest and enthusiasm in managing different activities associated to this digital platform on which we all are connected this evening and also would remain connected with the entire duration of 5 days of this workshop. In last but not least, I extend my warmest welcome to all the participants belonging to different parts of the globe, irrespective of their different time zone, who have registered for this workshop, and hope that this 5 days workshop will be beneficial to all of you. Now, in the continuation of further proceeding, first of all, I would request to the chairperson of REHS 2020, Professor K.L. Vaishnav, to share a few words for the audience. Professor K.L. Vaishnav, please.
Good evening to all, and good mornings, good afternoon to all. as we're connected across the globes. At the very outside, on the behalf of Department of Electronics and Communication Engineering of NIT Silchar, I welcome all of you in this August gathering. I welcome our Honorable Director, Sir, Professor Shivaji Bandyopadhyay, Dean of Research and Consultancy, Professor M. Ali, then our coordinator for this program, Institute Coordinator, Professor U. Kumar, and already Taimur has really welcomed all other dignitaries across the globes. We are very happy to see all of you in this pandemic situation, despite there are a lot of challenges in your life and around your surrounding also. But you all really given time to share your experience to all of us. As already said, Dr. Taimur, there are around more than 700 people connected across the globes. I'm very, very happy to be part of that. This big gatherings because our students of other universities, and really that will boost up the relations. And coming to this department, that's that the department started. Department started in the year of 1984. We remain undergraduate education until 2004. After that, we started our all PG and PhD programs. And initially started with our strength was around to be 60, 70. Now we are more than 200 faculties and really across the different specializations. We have coming to departments, we have a different specializations. We have BLSI, very large scale integrations circuit, and then we have a MEMS designs. We have a RF. Already said that RF has a big units. At a good number of faculty really they are working on the RFs. We have the signal processing unit. Then where there are a good number of people are working on the signal processing. Then we have communications across the antennas and all other taking microwave. So we have presently we have more than 30 faculties working with the different domain of specializations. I welcomes really all other experts also to have a more collaborations with the departments, because department, if you see the faculty age is a middle age around more than just 30 plus, so there is a huge potentials and huge opportunity to explore the faculties to collaborate with the different universities, different institutes, so that we can grow together. And presently we have a good number of international projects that NIT is running. I'm very thankful to our directors, present directors, Professor Shivaji Bandyopadhyay is really motivating young faculties to collaborate with the different universities across the globes to have more projects. This year we got 5 international projects across the globes. We are expecting in the coming years we may have more number of programs and collaborative projects. We have, despite this, we have several projects in the department from the Ministry of Higher Education. Then we have a Department of Science and Technologies. I hope that really with your support and collaborations in the future we can have a more projects. And as I said that presently the department has more than regular 100 number of PhD scholars working in different domains of engineering, electronics and communication branch. And we hope that since we have more than 100 PhD scholars working and good number of the publications, I hope so that there is a great opportunities. And I appeal, I request everyone, please, if there is an opportunity, please we can have a more collaborative project with us. As there is a number of speakers on the line, then before taking much time, I will say that really the gate is a great opportunity for all of us, and it's an honor for the Department of Electronics to be associated with this sort of international programs. Really, I thankful to all. I thankful to our organizers. I must thanks to the Taimurs. Really, he is working hard and he has connected the peoples. I hope so the near future we can have a more number of connecting projects with us. With this, I congratulate the Taimurs, his entire teams, and as he already said that Delhi Institute of Technology, what are Delhi University, presently we say Professor Ashok Desai is there, and then again our Queen University is also being connected. I really extend thanks to all really professor. I've seen that there are very senior professors also there. I'm very happy that the Taimur is really connected with all of them, and we are looking forward to have more project in the different domains of electronics and communication engineering. With this, I conclude here. Thank you, please. Thank you, and namaste, please.
Thank you, Professor Vaishnav. Next, I would like to call upon the Institute Coordinator SPARC, Professor Upendra Kumar, to speak a few words for this gathering. Professor Upendra Kumar, please.
A very good evening to all of you. Actually, this first I will tell about the SPARC program. So that is a scheme for promotion of academic and research collaboration, that is SPARC. So last year we applied for about 16 projects, and out of this we were able to get 4 projects, and this is a part of that one. That is the coordinator, Dr. Khan is the coordinator of that one. One coordinator, our directors is also there, so that we have had one workshop in the month of December, and now this is the second one, and the rest 2 researchers, they are trying to start the project. They have started, but the workshop is to be started very soon. So this workshop is in collaboration with Delhi Technical University and Queen's University of Kingdom, Canada. So I thank all the expert members of these institutes that they have made this program a great success, and I also congratulate this Dr. Khan and his team for the efforts to make this program, this workshop, a great success. And I also welcome all the participants, students and faculty members and the industry persons for this workshop, that is energy harvesting. And I wish this workshop a great success. Thank you.
Thank you, sir. Thank you, Professor Kumar, for your kind words. Now, I would like to invite Dean Research and Consultancy, Professor M. Ali Ahmed, to deliver his speech for this virtual audience.
Yes, Dr. Khan, thank you. Am I audible? Hello.
Yes, sir, you are audible, sir.
Okay. Very good afternoon or good evening and good morning to all the participants of the workshop. Respected Director, NIT Silchar, Professor Shivaji Bandyopadhyay, Professor Yahya Imam Antar from Queen's University, Canada, Professor De from Delhi Technical University, our HOD, EC, Dr. Khan, other experts, national and international, all the participants of the workshop, a very good evening and good morning to all of you. I am extremely happy to be a part of this workshop in the inaugural session. As already Dr. Khan has shown that about 737 participants are connected in this workshop or participating in this workshop. This would have been never possible in physical workshop if it would have been a physical workshop, and this may be say is a grace in the guise. That is only because of pandemic situation this has been happening. It is possible. Otherwise, this much gathering would not have been possible. Thank you again for participating in this workshop.
Thank you
As
very much, sir.
yeah, as you know, we have our institution has 4 SPARC projects. Other than this 4 SPARC project, as a Dean of Research and Consultancy, I want to share with some of the data of the institute. It is we have at present more than 50 numbers of national and international big projects are running in our institution. Out of that, more than 54 are SPARC projects. So this workshop is part of one of such projects. In addition to this, to promote our research culture in the institute, we have undergraduate research council. We are conducting Anveshan, that is called a research conclave, every year. So through this program, we are actually inculcating research and we are promoting research to our students and the students of the nearby university and in all other Indian universities. As of now, we have more than 600 PhD scholars, out of which about 450 regular PhD scholars in our institution. We are producing about 60 to 70 number of PhD per annum as of now, and this rate is increasing every year, as all of you are knowing. So, as a nutshell, I want to say that our director sir and all the institute authority, we are promoting all the scholars and all the faculty members to write project and to get the project from national or international fund. And we will continue to do that. Through this platform, I will again request all our faculty members to go for more and more number of projects so that we can, one hand, we will be enabled to have more funds, and on the other hand, we will have more JRF and SRF in the institution. This workshop, other than anything else, is a living example of interdisciplinary research, which is also motto of the present world. So with this information, I would like to thank all the dignitaries, all the participants of the workshop, and welcome to this workshop as a whole. Thank you very much.
Thank you very much, sir, for your motivating words. Now, I would now take the pleasure to invite our respected director, Professor Shivaji Bandyopadhyay, sir, to address the gathering.
First of all, a very good morning to Professor Antar, and either early evening or late evening to all other dignitaries and my colleagues also who are present in today's inaugural program, either in the Google Meet or those who are present in the YouTube live streaming at the same time. Yes, it is true that the current pandemic situation has made it possible for all such set of dignitaries to be present on one dais. But I understand all of us are missing the warmth of the, if there had been a physical meet here and the green campus at the same time. So I welcome, that is, I believe that there is light at the end of the tunnel. So when we will be able to see the light, when the current situation will be over. So it is the one welcome from invite from our sides to all of you to make a visit to NIT Silchar, again to see the campus, to feel the pulse of the campus itself. Now, to give an idea, that is about the National Institute of Technology Silchar, So out of 31 number of NITs in India, in terms of national ranking, we are 9th at the current level. In terms of technology institutions, we are 46th in the position. We are moving up, but I think there is a lot more miles to go before all of us can sleep and take rest. So life or the research path, academic path is a continuous journey, and all my colleagues, the students, scholars, the faculties, and others also, all of us taking that path. The next point that I would like to convey or share with you is that in all our research activities, the Sustainable Development Goals of United Nations, so that we have kept as our motto. So whatever activities we are doing, whether it is in the smart city or the infrastructure domain, or whether it is the communication domain, whether it is the multilingual activities, whether it is the healthcare one. So in all these cases, our motto is basically the 17 sustainable goals framed by United Nations, and which the government of India has identified as its development goals also. So with that path, so we are progressing, so that our research activities and based on the research activities that are taken care of by our faculties and scholars, we have some center of excellence areas, like say, of which energy is one area, then medical imaging and technology is another one, water resource is another area, and obviously natural language processing, the area to which I personally belong also, that is also another one. And in all these areas, we are trying to promote research activities, both at the national as well as at the international level. Now, at the present moment, say, we are basically streamlining all our research activities in the cyber physical architecture. That is where, as you know, that there are sensors which are distributed across the fields from which the data comes, and through wireless communication or the IoT devices, they basically go to the cloud computing environment. And the theme for these workshops, SPARC workshop, like the RF energy harvesting system, is basically more appropriate for these sensors, as well as the wireless communication systems and the IoTs also. So when we look into the domain of the cyber physical system, and we look into the main theme of this 1 week long SPARC workshop on the RF energy harvesting systems, we see that there is a matching, or there are overlaps, and that shows that the focus that we are currently having on the cyber physical systems and streamlining all our developments in that domain. So I think this is the right workshop, right opportunity for all of us to share it. And finally, before concluding, I wish that, okay, that I understand that is without this current situation, it would not have been possible for us to accommodate or to have so many dignitaries in one platform. But I do believe that in the near future, that is our collaborations will grow. So not only with our SPARC foreign PI and his institute, Queen's University, not only with the Indian co-PI, Professor Ashok De and Delhi Technology University, but also the dignitaries from the other institutes who are the distinguished speakers of this 1 week long program. So the relationship will be able to continue for further also, so that we can contribute to the society as academicians, as engineers, what we need to do. With these wishes, I wish this workshop a grand success. Thank you.
Thank you very much, sir. Thanks a lot for your kind words. Now, before concluding myself, or before concluding this inaugural session, I would like to invite my foreign PI, Professor Yahya Antar, to say a few words about his overall experience the first day when he was associated with this SPARC project, to till date. Please, sir, few words for the gathering based on your own experience after involving in this project.
Good afternoon or good evening, everybody. And I'm really humbled and honored to speak to all of you. First of all, I would like to thank the directors and the respected officials of NIT and Silchar for organizing and giving this opportunity. And I would welcome my colleagues from other institutions. And I'm really impressed by the effort of Taimur in organizing this. And remarkable thing, we have 734 registrants. So I welcome them all, and it's really a very good opportunity for us to exchange ideas and so on. The SPARC program is actually it's a brilliant idea for exchange of ideas and for collaboration and so on. And I see that the ministry is giving it quite a bit of attention. And I actually attended a meeting in Ottawa last year where there were representatives from the ministry and from the Kharagpur, where the program is administered. And I see it is giving quite a bit of importance, rightly so. Thanks to all, and I look forward to a week of exchange and activities and so on. It is great that you all giving it that effort, that importance. And if I just take an opportunity here and reflect on the number of participants, this is actually twice the number of the members in the whole Canada of the IEEE antennas and propagation members. If I put on a hat of the IEEE president-elect, I think this is wonderful. I've been to many places in India. And visited many places. I have so many friends there, and I have cherished the association with some of my colleagues there. Some of them are presenting in this conference right now. But I see quite a bit of potential here. According to IEEE, India's community is growing faster than anybody else, and you have more young scholars than any other region I see around IEEE. And what is that saying is that the future is great for this area of technology that is very important to all of us. So I salute that. I salute the young scholars. I salute the efforts that's taken by everybody. On behalf of my colleagues at Queen's University and Royal Military College, I thank you all for giving us this opportunity. One final note I should mention is that this workshop is just an initial step, and I echo the comments said by my respected previous speakers. This should be an opportunity to establish collaboration, to learn how to connect, to learn about the new direction of technology, and to know how to benefit. So it is an initial step towards future endeavors in terms of world and science, international exchange, collaboration, and so on. And through that collaboration, and will, future will be more brighter for all of us. So thank you again very much, and I look forward to a week of activities, and I look forward more to physically, hopefully in the near future, visiting the institute and visiting other places in India, which I always enjoyed in my trips there. So thank you very much, and I look forward to a week of activities.
Thank you very much, sir, for your kind words. Now, finally, I would like to call upon Professor Ashok Dey sir to say a few words on the overall activities of SPARC project going on. Hello, Professor Ashok Dey sir.
Good afternoon and good morning to everybody, all the participants of this program. Firstly, I am very thankful to Director NIT Silchar to organize this valuable program under this SPARC project. It is part of the project and it was necessary to organize this particular program. And really, Dr. Taimur Khan has done a great job by organizing, by collecting so many people in this pandemic time. And I know that it is very difficult to organize this type of program. And this particular program really gives a fresh air to all of us, because all of us are confined to four walls of the room for the last 4-5 months. And this is the opportunity to interact with all the international collaborators. And I'm sure that all the participants who have registered, and quite a big number of participants are there, and they will be greatly benefited through this particular program.
ब्रेक ना देते हुए शेड्यूल देखो ना, 10 मिनट का ब्रेक था अभी, उसको कंटिन्यूशन करेंगे। कितने बजे शुरू होने वाला था ये? 6:10 ठीक है। कैंसिल होते ही स्टार्ट कर दें। कर ले, वहाँ पे वो तो नहीं, उनको कुछ उसको बोलना डिस्कनेक्ट मत करें ना। अच्छा, डिस्कनेक्ट इसी में करें तो क्या करें, लेक्चर शुरू होगा तो इसी में।
I thank everybody.
Taimur, please mute your microphone. Taimur, please mute your microphone.
इसको दिए नहीं हम। हाँ ठीक है, इसी में कंटिन्यू कर लेते हैं। कोई सही बात है, वो डिस्कनेक्ट करके कनेक्ट तो कनेक्ट नहीं, हम अलग था और उसका अलग था।
Thank you all for.
Thank you very much, sir.
Thank you all.
Thank you, sir. Thank you very much. Now, finally, I thank you all once again for joining us this evening, as well as this morning, for the inaugural session of 1 week Indo-Canada workshop. We will take now the first lecture session, as we are already 10 minutes late. Then without further delay, I would like to invite Professor A. Alphonse to start the lecture session. Professor Alphonse.
Yeah, I'm going to share the file.
Are you comfortable to start right now? Because as per schedule, 10-minute break was there, because we are already running 20 minutes late.
Right, yeah.
Yes, sir. If you require, then you can take a break of 5-10 minutes as per your convenience. If you are comfortable, then you can start.
I can start.
Okay, thank you very much.
Is the screen visible now?
Yes, it is visible.
The PowerPoint file?
Yeah.
Okay, now it's what's the time? It's 8. Okay, here it is, almost in the night, 8:50. So rather than say good morning, good afternoon, good evening, I'll say just good day. It covers all. Okay. Thanks for the NIT Silchar, and as well as Delhi Technological University and Queen's University, Canada, for organizing this wonderful virtual platform workshop for 5 days. And I'll just straight away go into the technical stuff, because people have already discussed about the SPARC program, and then all these virtual meetings. The topic which I'm going to share, or the materials that I'm going to share with you all now is metamaterial-based RF energy harvesting. This is the way I plan my the talk, outline of the talk. I will just spend some time on introduction of energy harvesting. Being the first talk, I think I will take some time on energy harvesting. And then how the metamaterials can play an effective role in getting the good aperture efficiency or making the antenna to be very compact. So for that, some of you must be familiar with the metamaterials, but for the sake of such a huge participants of 737 or so, I believe that some of them are not familiar with the topic on metamaterials. So I just try to give a glimpse of 15 to 20 minutes on introduction to metamaterials. And then I'll go to the work which we have done. It's one of my current PhD student when he was doing masters. He did this, and then some of the work, I think is all commonly did by myself and as well as our student, and as well as Dr. Nazimuddin from Institute for Infocom Research. And then finally, if hopefully the time is there, I think I'll try to share how the metasurfaces also can have some enhanced impact on the energy harvesting or of energy harvesting. Okay. Then just conclude the talk. Okay, the first one on the introduction of the energy harvesting. We know that the wireless sensor nodes in the current smart cities, IoTs, there are various sensors are going to be deployed both at the indoor and then as well as the outdoor environments. And these wireless sensor nodes and as well as not only the wireless sensor nodes and the consumer electronic devices like a wearable electronics, it provides basically a gateway to the future and as well as for the smart world or smart cities. Okay, that's the way the whole technology is more driven towards. The 5G or the 6G is already started, and is all trying to have 6G is basically looking at the chip-to-chip communication or a short distance range communication, which is going to be deployed maybe in another 10 years or 9 years. Okay, so the future IoT and then future smart city developments, these wireless sensor nodes are playing a very important or essential roles. But the demand for the wireless sensor network is getting increased because they're going to deploy thousands or millions of sensor nodes around the places. So as the number gets increased, the need for the external power supply is also dramatically getting increased. Okay. Besides the problem of recharging, because if the battery is there, you need to recharge because the life of the battery is always a short time, okay, depending on the usage time. Besides the problem of recharging and replacing the batteries, the size and weight, or the more important thing for batteries are exhaustible sources with an adverse environmental effect. Okay, because the sensors might be deployed in some harsh environments or places where the natural disasters are happening. So for these reasons, it's highly desirable to find an alternative solution in order to overcome these power limitations. Okay. So you can see here in this one the various scenarios where the wireless sensor nodes or the wearable electronics are being used, and they may get charged by this kind of radio frequency energy harvesting. So basically, the environment represents relatively a good source of available energy compared to the energy stored in batteries or supercapacitors. Okay. In this context, energy harvesting, also known as sometimes some people call as a power harvesting, or some people call as energy scavenging, okay, is an alternative process for primary batteries where energy is obtained from the ambient environment. Okay. So as energy harvester typically captures the energy and then accumulates, stores, and manages the ambient energy in a proper way or more efficient way. These ambient energy is getting converted into electrical energy for autonomous wireless sensor networks, or the use of energy scavenging minimizes the maintenance and the operational costs. Therefore, the batteries can be eventually removed in wireless sensor nodes, batteryless, but there should be a the bias source for the ICs or the circuits inside by powering up by the this kind of techniques, as well as the portable electronic devices. These are some other scenarios. There are many potential ways, not only the RF energy harvesting, there are many potential ways to harvest energy from environments, okay, which are available, including solar and wind powers, and of course the radio frequency, which we are going to talk, and then the ocean waves, wherever the energy is there. Okay, the energy is there everywhere in different forms, right? Why don't we exploit those energies and then use it for some applications like this, and even the thermal energy and some mechanical vibrations. And when these kind of energy, there are a lot of publications, if you see in the literature, there's an empty number of papers on this topic, which has given a lot of attention to a great extent. And many papers have been published. If you try to look into the energy, just general energy harvesting as a feasible alternative to the batteries. Remember, one of the groups proposed an autonomous sensor powered by mechanical energy coming from the airflow or velocity. Okay. Therefore, a batteryless sensor uses the power harvested in order to provide the measurements of air's temperature and velocity by measuring the equivalent electrical voltage or the frequency of the wind equivalent electrical one turbine generator output. The wind speed measurement can be indirectly obtained in somehow. Okay, so based on the sensed wind speed information, the fire control management systems provides us spreading conditions of the wildfire, so that the firefighting can be deployed. Experts can immediately go there and then take a measures for that, adequate measures for suppressing those kind of the wildfires. Okay, the wildfire has become quite common nowadays because of the climate or green effect changes. So this kind of energy harvesting can provide a wonderful solution for them. Okay. And we have seen that this this slide shows that. Let me put there's a pointer. Okay, the various energy sources, like just I mentioned, as a kinetic energy or a thermal energy, or the what we are going to talk on, the electromagnetic energy. This need to be converted into an equivalent electrical signal by appropriate transducers or a sensor. And this is all time varying signals, because all the vibrational energy or thermal energy, it's not fixed or kind of a constant with respect to time. So it's all time varying signals. So it needs to be converted into an equivalent to DC. So AC DC conversion to be done. And finally, if it is very high, and then DC to DC conversion also to be done for appropriate recharging devices, because some of the devices may not need a very high power, like the sensor nodes may need a microwatts, or some sensor nodes may not be operating continuously. It may be operating at a certain time period. So only during the time the battery need to be used. Okay, so this table gives a kind of a comparative informations about the various energy harvesting sources. If you look into this, these are the sources which we captured: the solar energy, the thermal energy, and the RF energy, and then the piezoelectric and the vibration one. Okay. If you see in terms of the power density, here the solar has got a very good amount of the power, based on, if you try to see in terms of the density per centimeter square, because you get a direct sunlight, the intense sunlight, you get a very good absorption of by the solar panels, and then able to generate the output. And then solar energy has been used for various applications. Okay. It has been a well matured technology, and then now only the bottleneck is how to enhance the efficiency of the conversion efficiency of the solar energy into the equivalent electrical. There's a lot of the semiconductor electronics group has been trying with the various devices and various heterostructure configurations how to enhance the efficiency of the solar cells. Okay. In terms of the power density for the thermal energy also quite reasonably good amount of power, which is Typically 1 centimeter square of 100 microwatts could be extracted. RF energy, which is very low, but it could be sufficient for our desired applications, like what we are talking about, the wireless sensor nodes or some of the consumer electronics or wearable electronics. Okay, typically in the order of microwatts per centimeter square. Okay. The vibrational one, which is 200 microwatts per centimeter square, and then push button means it's kind of pulsed vibrational energy, which is 50 microjoules. Okay. The output in all these scenarios for a solar energy one, which could come around for in terms of volts, or roughly maximum 1 volt with the silicon cell, which is quite mature technology. Also, silicon technology now people are trying to use. GaN also, the wide band gap semiconductor is also playing a role for some of the solar energy conversion applications. Okay. So we don't have a data for the thermal energy output, but it varies because though it's available, always available, but it gets varied because of the intense heat and then the variational with the time. Okay. RF energy, it's able to give roughly 3 to 4 volts with the open circuited conditions, but with the loaded condition, it might come down. Okay, we'll share some of the results of our investigations. Okay. The vibration energy can give a much very high output voltage of 10 to 25 volts, or even the push button one can give a pulsed energy, so it's very high, kilo in the order of a kilo also is possible. Okay. In terms of the availability, the solar energy it's a daytime, so if you try to see the global, some countries have got a less number of sunlight, some cloudy days, foggy days, or rainy days. It may not be possible to use their solar energy conversion, so the time is restricted. The tropical countries or below subtropical countries, Southeast Asian area, or even South Asia, you get intense amount of solar energy for a longer time, where solar energy is getting picked up. And that's why you could find in those places solar panels are getting popular. So it's typically 4 to 8 hours. Thermal energy, it's always there, the temperature, so it's a continuous one, and again, it depends on the zonal or region-wise. Okay. RF energy is available anytime or continuous, right? So whether it's day or night, all the time, RF energy is available. The piezoelectric energy based on the activities. So whenever the vibrations are manually excited, okay, some kind of a piezoelectric way, I think some vibrational effects to be initiated for this. So it's basically an activity dependent. If you look into the advantages or merits of all these energy harvesting sources, solar definitely has got a large amount of energy because of the sun shine, the intense sunlights. Okay. The thermal energy is always available. That's one of the advantages. Or the RF energy is omnipresent energy with a variable, with the various RF sources available with different applications, which I'll show it later. So well-developed technology is there for the piezoelectric energy. That's a matured one, and that's a big advantage for vibrational energy. The drawbacks or the bottlenecks for all these energy harvesting techniques, if you see, it's solar panel needs a very large panel. You must have seen it. It needs to get a certain amount of 1 volt out of this single silicon cell, and they need to be combined to get enough output for certain applications with heater, water heaters, or from the indoor lighting. People use it, but it is a large area to capture the solar signal, because of the conversion efficiency has been very poor, okay, 15 to 20%. Some literature paper comes out with 25%, but not sure whether they're able to have such kind of very high efficiency. Okay. And then the orientation, a solar panel has to be always the conditions where the orientations. And then thermal energy, it have again large panel area, but the power output is very low. RF energy, the drawback is the distance. Okay. As we know that the electromagnetic energy gets decayed by exponentially getting decayed. So as we go a few tens of meters, the drastic reduction of the electromagnetic energy or the power, which makes it sometimes very difficult to. So you need to really pump very high power to reach out to the the longer distance, about far distance. Okay, that's one of the drawback. But nothing is perfect. One has got some always some advantages and some disadvantages depending on the applications, or dedicated applications, or desired applications. One need to go for it. Okay. The vibration of the piezoelectric also, the output is sometimes very low, because you can see that the output is 10 to 25 volts, but it needs a very large area to get such amount of volts. Okay. And then it's highly variable output also. Okay, so this talk basically focuses based on the theme. It's on energy harvesting technology using the electromagnetic energy captured from multiple available ambient RF energy sources. When you say ambient, it could be a dedicated RF sources, or it could be ambient RF sources. Okay. Dedicated means it is desired to power up certain devices. Ambient means you don't need to. It is used for communication purpose, as well as you're trying to extract the energy from that. Okay. Because even when the RF power devices here, you can see the information flow is there, so the data is going for information transmission zone within that, and it can reach out even much beyond, but because that operates based on the bit error rate, because the receiver sensitivity of those mobile phones are very less. Okay. So the wireless, when you try to see the energy transmitters, it could be a cellular base stations, transmitters of the microwave relay stations, wireless routers, user devices. Even one of the user devices can be a potential source to the other devices. Okay. And if you try to see an external, it's a satellite transmitters also can be used up for your powering up. The radar, FM and AM transmitters, and some dedicated RF sources. Okay. So all these play kind of a potential sources for our energy harvesting, especially when this is infrastructure based architecture. When you see the other side is infrastructure less architecture. That means we don't have really those base stations or dedicated sources, but you can use it up from your ambient transceivers or any of the device. RF powered devices itself can be a potential transmitter, okay, to the nearby devices. So this doesn't need any big infrastructure configurations. So these available sources, like this technique, is very useful for sensors located in a harsh environments or remote places, where other energy sources such as wind or solar sources are impracticable. Okay. Okay, let me move on to the next slide. So the interest in harvesting the ambient RF energy in recent days is becoming very good attention because of these following reasons. The ubiquitous presence of RF signals from the digital televisions, radio, and satellites, as you mentioned in the previous the page, the wireless local area networks, and the cellular networks. Okay. And then the advent of the low power electronics, where the AC to DC converter or a DC to DC converters are getting popular in the power electronic side. So that also made a resurgence of interest in using RF signals very efficiently to get the desired output voltage. And the most important thing is the need for green, self-sustainable electronics for very low power applications, such as for Internet of Things devices. Okay. For the future smart cities. Okay, so when you say that all these the transmitting signals from various sources, AM and FM transmitters has got a very high power. I have one slide maybe later next to this. I'll show it. As we all know that when you try to calculate the power received by the receiver, receiving devices or a RF power devices, the very standard formula is the Friis transmission formula, which we have been using it for all the electromagnetic wave propagations. Okay, so this everyone is familiar with this. This is the power received, and this is the power transmitted. And then the power received power is depending on your transmitting gain antenna and the receiving gain antenna and the frequency of operation. and the distance, and this is the last factor. Okay, because you have exponentially the signal is also getting, so you need to account the path loss factor. Okay, but this is the line of sight. Okay, so, but the signal that you receive in a real environment like indoor or even a places where you have multiple reflections are happening. Okay, so you need to accommodate the multiple multipath effects also. Okay, so this also people must have seen it. Those who have done the work on multipath propagation model for the electromagnetic wave energy in free space. So this is the transmit power. The only the difference is you have it goes out by the fourth power. Okay, so the signal becomes weaker. You can see because when the distance is becoming longer, this is d square. So it also depends on the height of the transmitter and the height of the receiver that is being used in this model. Okay. So one has to calculate or very rough calculations when if we want to make it, how much power can be received at a certain distance. One can use this as very simple expressions to find out how much power is getting captured by the RF power devices. Okay. Yeah, so this table shows a rough idea about at what distance you may get the amount of power captured by the receiving device. This I got it from one of the telecom magazines. So it's a 50 kilowatts AM radio station. Nowadays we don't listen to AM radio stations. We all move to the FM radio, and even many don't listen to FM. They go to YouTube's, and then YouTube is also all through the Facebook. I think all the radio stations are getting broadcast. So hardly people receive or use the radio to receive the signal. Anyhow, the signal is available. Still the radio station transmitters are there. So since it need to travel over a longer distance of 60 to 70 kilometers, around the distance of 5 or 10 kilometers, you can see roughly the power density available is 159 microwatts per square meter, and then 40 microwatts per square. But then the receiving antenna, we don't make it like 1 meter by 1 meter. It would be on a centimeter by few centimeter by few centimeters. So you can see, you can compare it, how much power can be captured really from the AM radio stations. GSM base stations, I think this is the 2G systems, I think. Yeah, 2G. So some of the 100 watts GSM base stations were in the order of kilometers. If you try to see the power available is 8 microwatts per square meters. Again, it's very, very small. The mobile phone, which transmits in the range of 10 meters, if you have any power up device in your smart home, it can provide around 4 milliwatts per square meter because the distance is very short. It can have. Okay, so the potential source could be this rather than all these the base stations and the radio stations. Okay, and the Wi-Fi routers, which we use it in our home. Okay, typically in the order of 1 to 10 meters, we can have 80 to 84 milliwatts per square meter. Okay, this is the rough estimate of the one, because we use Singapore has been completely wired up by the fiber optic network, and all the residential units have been connected by the fiber. The fiber comes up to the drawing hall, and from there we have a Wi-Fi router which covers up all the rooms. Okay, or we can have a booster if your residential unit is relatively bigger, you can have another booster unit within the residential area, another Wi-Fi router, which can provide a wide coverage within that. Okay, so this Wi-Fi router will be continuously transmitting the signal. We might be seeing it keep on blinking, means I think keep on sending the signals, and then the energy is getting really wasted during the time which is not really being used. So one can exploit this for this energy scavenging or energy harvesting applications. Okay, let's with this basic introduction, let's go into more detail about the schematic. The basic structure of a radio frequency energy harvesting system consists of the first thing is a receiving antenna. The front end part is the receiving antenna. Without antenna, you cannot capture any EM signals. So a receiving antenna, and then the antenna impedance has to be properly matched. Otherwise, we know that all the signals will get reflected back, and improper matching makes it really very impractical usage of the whole system. Okay, so the matching circuit is a very important one. The antenna should be properly matched with the subsequent devices or subsequent matching circuits. I mean the rectifier circuits or the loads. Okay, so the matching network and then rectifier circuits are nothing but diodes, right? We must have seen for a very simple FM capture or AM capture of the signal, we use envelope detectors. Okay, envelope. So it's a peak detector. One could use a diode, which I'll come down more detail later. And then this signal may not be sufficient, as I mentioned earlier. At such a large distance, when the signal travels, it gets exponential decrease, and then you have hardly microwatts level of energy with such a small aperture area. You must have enough voltage to boost up or to power up your sensor nodes or wearable electronics. So one way is to elevate the voltages. Okay, so you need to elevate the voltage by doubler or a tripler or a quadrupler. Okay, so I'll show some examples later. So there's some voltage elevator, and then finally it delivers to the load, which whatever it is connected. Okay, where electromagnetic waves are captured here. You know that antenna is the one which captures the energy. The voltage can be amplified through this, and then it's really thanks to the peak detector, because envelope detector, finally the voltage output is getting adjusted using a voltage doubler or voltage elevator. Okay, so the whole system is formed by it may look very simple on the block diagram, right? So the whole system is formed by a receiving antenna, a matching network, and a rectifier. Usually it's called as a rectenna, because if you can integrate the whole thing in a same layout or a printed circuit, which is able to harvest the high frequency energy in a free space and convert it to DC power. So the whole unit is called a rectenna, rectification antenna. Okay. Further to this, it's not the end. A block power management and energy has to be stored, right? Sometime when the sensor nodes, as I mentioned in one of the earlier slides, that the sensor may not be operating continuously. Whenever it need to send the data to access points, nearby access points, it need to operate. So other time it will be sleeping. Okay, during the sleep node, if the energy is getting harvested, how to store it? Okay, so that's more important. Also, the energy storage could be integrated into the energy harvesting system. So the energy storage subsystem is responsible for storing all the captured energy and providing a constant output voltage whenever it is required. Okay. So the energy harvester is a promising power solution for wireless sensor nodes. Instead of depending on centralized the power sources for charging the sensor devices, which operate at some of the existing energy in the environments. Okay. The DC voltage is typically stored in a capacitor or a supercapacitor in order to power supply those integrated circuits housed in those sensors nodes. Okay. Okay, let's go by one. The first one is an antenna, right? So let's discuss about the antenna. Okay. I think Dr. Nazim is going to discuss more in detail about the antennas for the energy harvesting. So I'll not discuss what kind of antennas are typically used, but I'll just spend a little brief so that there is not much overlap. Being the first talk, I may be overlapping with many talks, so I have a little advantage of others. Okay, sorry for it, but anyhow, so it's okay. So we know that antenna, the input impedance has to be properly matched with the load. Then only it's the energy is delivered to the load appropriately. So the RF energy harvesting technique needs, as I mentioned earlier, an efficient antenna with a circuit capable of converting alternating current AC signal or AC voltage to direct current voltage. So the front end is a very important, or essential, or a key component to ensure the successful operation of the entire system. Okay, so that's why the antenna community has been really working very hard, and then you could see a lot of papers from the antenna community or antenna research community coming out with the various types of configurations on antennas to enhance efficiency, to enhance the aperture efficiency, all that. Okay, so it has a duty or a responsibility of capturing the electromagnetic waves, which will be used later to power up the integrated system. Besides this, the antenna efficiency is related to the frequency. Energy obtained from the antenna with a small bandwidth or a very narrow bandwidth than the wideband receiving antenna used to capture the signals from multiple sources. If you can design an antenna like a dipole antenna, this example I've shown it here, it's a very narrow band. Even if you take a microstrip patch antenna, it's also a very narrow band, and some of the antennas which could operate at a very desired dedicated frequency band, so it can really receive the energy only at that particular frequencies. So if you can design an antenna of a wideband or a multi-band antenna, knowing the variable available sources or of sources around the IoT sensors deployed zone, even for satellite. Okay, so quick signals come from satellites, which could be also captured in a much easier way. So that can be done also for a multiple access. So the RF antenna can harvest energy from a variety of sources, like as I mentioned, broadcast of TV signals. So you need to go for TV signals at the ultra high band, UHF bands. Mobile phones at 2G systems, 900 megahertz, 1800 megahertz. Okay. And in Singapore, we have phased out the 2G systems. So we have only currently 3G, 4G, and then 5G is around the corner already. Is going to anytime it's going to be deployed, but current with the COVID situations, the things are getting delayed. So anytime it's going to be deployed in Singapore. Okay, and then the wireless local area network with ISM bands at 2.45 and 5.8 gigahertz. So these all could be exploited. So you need to design an antenna which can cover up at least a few bands, if not all, at least few bands. Okay, so that's where all the most of the antenna community has been doing on the multi-band antennas for the energy harvesting. Okay. So this antenna, the equivalent circuit is shown here. In principle, the power harvested from RF signal is enough to supply the microelectronic devices. This is basically the load here. Gradually, however, this power can dramatically increase by using an array configuration. Instead of using a single antenna, if you can use an array of antenna, it can have the more gain, or which can provide the maximum possible power can be achieved by properly arranging a similar antenna with the same matching circuits and power management. Okay. So there, if you have an array antenna, then the problem comes with how you have the feeder network or a capture network. So all the feed line, the corporate feed arrangement, all need to be done. And if you have a multi-band antenna with the array antenna, so it need to have a matching properly with all those frequencies to different frequencies. So these are all the potential challenges for our community. Okay. So the trend is to include antenna, usually kind of a patch antenna. You can insert a slots or make a variable, the slits. That's a typical, most of the antenna research community has been doing on it. And with the appropriate rectifier on the same printed circuit board could be a good device. Okay. And again, making an array of antennas. If you make a large array of antennas, then the sensor nodes has to be really big, right? So that also the layout is a problem. Okay. Always it's a problem for antenna community, because people think that antenna community is a supportive unit for most of the communication projects. So I hope everyone agree that, because whenever you work with the people like the satellite group or for other group communication sensor network group and all, they don't provide any layout. When we say that we want certain layout for let's say for a CubeSat, this is my experience. So in our satellite research center, whenever CubeSat is getting designed, so they all come to us asking for a small antenna that could be fit into your CubeSat, because CubeSat is just 10 centimeter by 10 centimeter by 10 centimeters. So they have all the power up circuits, the sensors, and then all the other circuitry, control circuitries, all there. But when we ask for the space for antenna, they say, no, we have only this much space. Try to confine your antenna to that level. So they say, always say the antenna is as a secondary one. But when the antenna fails, the whole system fails, right? So antenna is a front-end element, is a key element. Just throw the satellite, and then if the antenna fails and if it's not able to capture, it cannot transmit down, the entire thing is gone. It's a debris only. Okay, so that's about antenna. I hope I am not discussing more on antennas. So let me go to the next one. on the impedance matching network. Okay. As I mentioned earlier, the matching network is an important element also, because the antenna input impedance has to be properly matched with the load. Otherwise, your the conjugate power matching may not be properly done. Okay, so the impedance matching network, it's basically a resonant circuits operating at the certain design for frequency or a designated frequency to maximize the input voltage of rectifier circuit by reducing the transmission loss between the antenna and to the between the antenna to the rectifier circuit, or to the device where you want to convert or store the energy. Okay, so this basically maximizing this kind of maximizing can be achieved when the impedance of the antenna is when the antenna output is conjugated, right? Conjugated to the impedance of the load, so that you can compensate all the reactive parts. Okay, so this matching network is usually made of reactive components such as coils. Here you can see one such arrangement, the coils. Most of the RFID, they try to use this kind of one, and resistors also, coils and resistors. And the other one is capacitors, or kind of a shunt one. Okay, shunt element also. And this another way, the capacitor. So this there are three matching networks. I just shown it. Yeah, kind of a transformer here, transformer one, and a shunt inductor, and a kind of a LC network. Okay, so this is possible to have a proper impedance matching. And then if you want to have a wideband impedance matching, you have to play with that with this kind of a lumped element components, the multiple lumped element components, to enhance the bandwidth of operational bandwidth. Okay. Okay, let's go to the rectifier circuits. Okay, the third element, which is rectification, because you have already matched the antenna impedance with this kind of a matching network, and then finally a rectifier is to be done. Okay, the rectification is nothing but it is basically used to convert the RF signal captured by the receiving antenna into equivalent DC voltage. We have been using a kind of a crystal diode for most of our applications in the laboratories. Okay, which is very cheap. Okay. One of the diode which is typically used in this energy harvesting system is a Schottky barrier diode, okay, which gives a very good conversion efficiency. Okay. The key challenge for the rectifier design is to generate a DC voltage from a very low power RF input, which is coming from here, right? Which we have been mentioning it frequently, very low power RF input. Generally, to get the higher conversion efficiency, diodes with the lower built-in voltage to be preferred. Okay, so basically there are the three main options for rectifier, or it could be a kind of a diode. You can see it here on the simple diode, or a kind of a two diodes, or a kind of a quad or bridge diodes. Okay, whatever possible configurations you can use it, or voltage rectifier multiplier. Okay, combined integrated one. Okay, so the main component of the rectifier, if you see it here, is basically a diode, which determines the performance of the rectification circuitry. Okay, so the rectification circuitry performance usually depends on the saturation current and the junction capacitance of your Schottky diode, and of course the conduction resistance, or the conductivity of the diode. Okay, so the most commonly used diode for the rectifier circuit is basically a Schottky barrier diode. Here the configuration is shown for a single diode here. Okay, this is these capacitors are basically to compensate the reactive part. Okay, to match the impedance with the diode. Okay, so two diodes, and then 3 and 4, 5 diodes. So you can see the voltage output gets increased because you have more diodes, you get a better output. Okay, but the efficiency is not the same, because when you keep on this is the input power. You can see the input power from minus 20 dBm to 10 dBm. Okay, so around 10 milliwatts. Okay, so this is 1 milliwatt. Okay, so if you try to see, the efficiency is not because when you keep on increasing, the diode is a nonlinear device, right? It's a square law device. So when you're trying to operate with a large input voltage, so it may go into the nonlinear board, and it generates some harmonics. Okay, intermodulation harmonics, as well as it may go to the saturation current output. Okay, so there is an optimum. So when one need to find out, not necessarily the 5 diodes can give a better, though give output, the efficiency may not be very good, right? The conversion efficiency, it's giving a good output, but extracting the more input from that. Okay, you can see the more output then give you more efficiency. So if you try to see around 0 dBm, around 1 milliwatt, you can see that most, whether it's a single diode or 5 diodes cases, it gives a optimum efficiency of 35 to 40%. So one need to really work on the SPICE model of this one: a single diode, double diode, triple diode, and then quad diodes, and then 5 diodes. And whatever number of diodes that you're going to use it, you have to first work it out with the SPICE model and then see which input could, or which could give a most efficient or most optimum one. Okay. Okay, that's about the general one. How much time? What's the time I've taken it? Okay, so 40 minutes. Okay. Probably I'm going very slow. So a lot of effort has been put into the research and the development of ambient or of energy harvesting sensors. So individual components are playing a role. Okay. So one of the important thing, as I mentioned earlier, sensor wireless sensor node is very small, and then always the requirement to make the antenna to be very compact. You don't have a layout to play with the enhancing the antenna efficiency. So I get a very good efficiency for such a massive structure, but no one is going to come with that. Okay. So you have to have a very compact, a low profile, multi-band, omnidirectional, and highly efficient. All are highly challenges, right? It's a multi-objective problem. Okay. So antenna community has been facing these challenges, and then they are coming out with the solutions. Okay. And then the next one is the matching circuit and rectifier should be compact and low profile and achieve the very good RF to DC conversion efficiency at the operating frequency bands. Okay. So the main objective is to make an antenna compact and low profile, and also the multi-band, omnidirectional, and highly efficient. Okay. So how to go about it? Okay. So that's where if you make a very conventional antennas like a patch antennas and dipole antennas, so it could operate at a single band, and then the structure could be very big. Okay, may not be able to accommodate within the sensor node layouts. So the metamaterials come into a very good supportive role there. Make it very compact because the wavelength, it's all going to operate at a very sub-wavelength technology, right? So I'm going to give just a few brief introduction about the metamaterials before going to the how we have used that metamaterial concept in our RF energy harvesting. Okay. Okay, maybe I'll just skip some of the slides as I've taken more time on the this one. We know that from 80s onwards, the concept of the photonic band gap and then electronic band gap materials have been popular, and because the periodic surfaces or the periodic medium concepts have been exploited to realize for a leaky wave as well as for reflections. Okay, and also it could use for some of the application like using artificial magnetic conductors or high impedance surfaces, all towards the periodicity is almost in the order of a wavelength. So the structure becomes so big or bulky. Using it for a commercial or a consumer electronic devices is becoming a very difficult. Though a lot of academic research community has brought out a lot of publications, or some of you must remember that before EBG, all the microwave community has started using PBG, photonic band gap. The reason being that first it started with the photonic domain, using the crystal creating voids, periodic voids in photonic crystals, which can be used in routing the optical signals. Okay, so the name has been coined photonic band gap, though the periodic structure has been there in microwave community since 40s, okay, or even before that. Okay, so photonic band gap materials have been typically used even by the microwave research community, but then a lot of objection even sorry. From the microwave community, especially from Professor Oliner. I met Professor Oliner in 1989, right? When I was in Osaka at that time, Japan. So I heard his talk on the periodic structures, and then I also worked on periodic structures. So I used to meet him at European microwave conferences as well as at some of the APS conferences. Okay. In '99 at Munich, he even called all the people to recoin the name instead of using, because there is no photonics involved in this. All this, you use patch antenna, create a periodic slots or periodical artificial magnetic conductors and high impedance surfaces where the photonics is playing a role there. So he insisted that you need to call that as a EBG, electromagnetic band gap. So then it became a term called EBG. So which is quite relevant. Okay. Okay, that's all quite big size with our EBG materials. Then the concept of the metamaterial, which was proposed by Vaselago. Many of you must be familiar with the name. Those who are doing metamaterials or at least got a glimpse of metamaterial concepts, who came out with the first paper on negative index refractions, just a theoretical idea of when the material has got a negative index of refractions, how the signal behaves or how the electromagnetic behaves. Okay. There the periodicity is when you make a periodical variations. Since the periodicity is much smaller than wave, because it's always play around the zeroth order resonance. So zeroth order resonance means beta is 0, the phase shift is 0. So beta is 0 means 2 pi by lambda. So lambda is infinity. So really the wavelength is not, or the dimension is not playing an important role there. So the elements and distances between them are much smaller than the wavelength. So one could go for effective medium concepts. So that really being exploited in most of the metamaterial or metasurfaces structures. Okay. So you can make the material constants or permittivity and permeability to be simultaneously, or one of them to be effective negative. Okay. So this can be called as a left-handed materials or double negative materials or negative index of refraction by the optical community or the backward wave materials. Okay. Yeah. So in this, what is the difference between a right-handed triplet and the left-handed triplet? Means you have the phase velocity of the wavefront, which is traveling in the positive direction, which is a conventional right-handed one, which we use it normally in our most of the transmission line or for the electromagnetic wave propagations. Okay. But in the left-handed triplet, these are opposite. The group flow, still the energy is traveling in the positive directions, okay, positive axis directions, but the phase front is going in another direction because it becomes a negative, the phase velocity, okay, or negative beta. Okay, so the Snells are also getting satisfied because we before the electromagnetic wave last came into our world, all the people who are using the ray optics, right? So the Snell's law have been still applicable there. And then when you try to see, whenever you have the incident ray here, there's a partial reflection because of the impedance discontinuity or the index refractive index discontinuity. It's a partial reflection, and the ray should be refracted or transmitted into this direction, right? But if it is a negative index, so to satisfy the Snell's law, the negative angle, so it should be in the other direction. Okay. So the people optics community started using for a perfect lens or perfect focusing. Okay. So all that work has been done by photonics community also exhaustively. Okay. So though I also met Vaselago in 2004. Yes, 2000. Yeah, I forgot 2003 or 2004. He brought a very big team, around 15 members from USSR. Okay. Okay, so it's Soviet. At that time, it's not so USSR, but still we are old people, so we still call USSR. It's from Russia. Okay, so he brought a 15 members team from there to. It was a kind of a very first conference or a kind of a small workshop at in Spain, just almost at the border of the Portugal. Forgot the name. It's somewhere almost at the end of Spain. Okay. So there I met him, and I had a good discussion with him at that time. And then I also started working on metamaterials from that time, and started applying metamaterial concept on the transmission lines and the leaky wave antennas. Okay. Okay, just quick. Some of you must have seen it, so I'll just quickly go through it. This view graph shows that it's a positive axis. Show that it's epsilon and mu axis. The vertical axis is the mu permeability, and then this horizontal axis is permittivity. So this is the area where most of us are working, right, with the double positive substrates. Okay, double positive means both permittivity and permeability are positive, and then most of the commercially available one is all positive only, right? Because the reference relative permittivity of the free space is epsilon r, or mu r is 1, so we all work around this region. Okay. Well, when you move to the second quadrant, basically it's the positive permeability and negative permittivity, which basically are plasma creations. Okay. This was there, I think, it's a long time, because the plasma and creating a free electron hole plasma. And I also did some work long back by optically exciting the semiconductor waveguide, silicon or gallium arsenide with the appropriate wavelength. You could create a free electron hole plasma within the substrate, and where the permittivity becomes a negative. Okay, permittivity becomes negative, so one could use it for some switches or phase shifting applications, because the epsilon gets changed by optical excitations. So one could go for the phase shifters, optically induced phase shifters at very high frequencies. Okay, silicon dielectric waveguides. So some of the papers you can see it in 80s, I mean late 80s and beginning of 90s. Okay. So that's one, and then this could be done even by having an array of thin wires, and then having a electrical field parallel to these thin wires. One could excite that, and then in the induced currents or the induced fields here at a particular frequency based on the dimension of the wire, and then the periodicity, it could have a negative permittivity display. Okay. And then coming to this quadrant, it's mu negative. Okay, this is epsilon negative and this is mu negative, but still epsilon is positive. Okay, so this also many of us must have seen it in the ferrite materials. Ferrite materials, because of the spin resonances at a particular narrowband frequencies, it could show a negative permeability. The kind of anti-resonance is there, so it goes back to the pole, and then it comes back to the again kind of a reasonable permeability to operate for isolation purpose. Okay, so that's in the mu negative. Okay, so ferrites could display this kind of image. So these are all like already existing one. Okay, but here mu negative can be also made possible by the experiments done by this the Imperial College as well as UCSD group, by having a SRR structure, split ring resonator structure, array of split ring resonator structures. Then magnetic field is in the axial directions. Okay, so this is all one of the parameters, material parameters is negative, either epsilon negative or mu negative. Okay, what will happen? Both are negative. That's what was like was question. Okay, that's what he did it in 1964, but he couldn't demonstrate it because of which the people were not aware of how to really make it double negative, because the conventional materials are all double positive. So how to make double negative? Okay, when this was shown by 1990, yeah, I think this was the earlier time. I think I'm not sure the animation is getting played or not, but you can see here the double negative material is getting sandwiched between a two double positive substrates. When the energy is traveling down through this, you can see that the energy is traveling still in the positive direction or the dizzy direction. So you can see the wavefront is getting pushed backwards. The phase velocity is going backwards, and then the energy is going in the forward directions. Okay. And of course, this is the Drew-Lorentz formula provides the negative index of refractions, and one could get this imaginary one could contribute towards your lossy behavior of the double negative material. But you can see here the intense on the double positive and the intensity, the gray scales are really low. Okay, though the energy is well confined within this double negative, because the energy is getting focused onto this, but the intensity is not that compared to this one, because it's really the lossy is coming from this part. Okay. Yeah, so this group, the Pentry Imperial College as well as the UCSD group, Smith and Schools, combined the structures, and then they demonstrated in. This is the first demonstration that double negative is possible by having a thin wires array as well as a SRR arrays. Okay. So anyway, I'll not spend much time on this. You must have heard this kind of a talk or this information at many places. Okay, I'll come down to this. So the metamaterials can be realized, but these all resonance structures. If you could see, this is very bulky, right? This is very bulky, and then it's not really usable in the really practical applications. Okay, so I need to make very. This is also very resonant one. Okay, this was demonstrated around the 10 GHz, I think. Okay, expand one. So we need to make a kind of a non-resonant structures. Okay. So to make a non-resonant structures, make the system to operate, or make metamaterials to operate over a wide range of frequencies, or a wider frequencies, or a broad range of frequencies. That's where our transmission line concept comes in. Okay, so make a transmission line, realize it, either in a microstrip or a coplanar waveguide or a CPS, or nowadays the substrate integrated waveguides. Okay. So you may see some of the papers from my group as well as for Dr. Nazim's groups publish some papers on substrate integrated waveguide based on Q-wave antennas or SIYW resonators, okay, zeroth order resonators or first order resonators. So these split ring resonators and thin wire, based on this configuration, it could operate only at a certain resonant frequencies. Okay, is at a very narrow band. If you want to make a non-resonance, make it over a wide band, transmission line approach is a better choice. Okay. So now onwards, I'll move on to the transmission line with a wider band or a multi-band operations, where the transmission line could be modified to make it like a metamaterial or a composite right-left-handed structure. Okay. What is composite right-left-handed? Some of you must be familiar with this term. Those who are not familiar, I'll just briefly mention about it and then go to the actual realization. Okay. As we know that it's a conventional transmission line, the equivalent circuit is this way, right? The series inductance and then shunt capacitance periodically arranged. It's a lossless transmission line, which I'm mentioning about it. And then the propagation constant is decided by your lumped elements or the equivalent circuit elements of L, R, and CR, the inductance and then capacitance, which is nothing but omega into square root of LC. Okay, this is the standard formula which we have been using it to estimate the approximate the phase constant of the wave which is propagating in the conventional transmission line. So this is the cutoff, and this is where your dispersion characteristics, which is beta, which is extracted from here, right? At the different frequencies, you get a beta. So this is the fundamental mode of your the signal which is traveling in this transmission line. Okay. But now we have to, if you want to make it double negative, your epsilon and mu should be a negative. Both the material constants to be a negative, double negative. Okay. So how to do that? Okay. Then you have to go for a left-handed propagation. So left-handed propagation means it's just reverse it. The series capacitance and shunt inductance. Okay, series capacitance, just reverse the configuration, so it becomes a pure left-handed transmission line. Okay, this is not new. When the people floated this one, I think many of us thought that it's new, but it is not really new. Those who have done the electronic circuits long back in their bachelors, or even some of the students are doing the electronic circuits, right? The phase shifters, the voltage, the phase lag and then phase lead circuits are basically these circuits only with the R and C and the C and R. Okay, there's just reverse configuration. Same configurations here, the phase lead or phase lag. Okay, so that's what it is being used here. So the pure left-handed transmission line here. So if you calculate the propagation constant for this, it's 1 over omega root of LC, because it's just reversed. So it becomes so. When you see this, it's like y is equal to 1 by x. It's a rectangular hyperbolic curve. You can see here it's a rectangular hyperbolic curve. So that's our dispersion characteristics of pure left-handed transmission. But how to make it? How to realize this? Our conventional one is a pure right-handed, so we cannot realize exclusive pure left-handed transmission line. The only possible way is use this conventional transmission line, or use a positive right-handed transmission line, embed this pure left-handed onto that. So making these two together, making a composite right left-handed transmission line. So your dispersion characteristics can be altered by moving into the desired zone of this region. Okay. Yeah, so this is where your composite right left-handed transmission line. This is the conventional right-handed host substrate, the transmission line. Whatever way you realize it, microstrip or a coplanar or a CPRs or substrate integrated waveguide. Now we introduce this series inductance, series capacitance, and shunt inductance onto this. It became a composite right-left. Okay. But if you realize this, this has got a series resonant and a shunt resonant circuit. So these resonate at particular frequency, LR and CL, and these resonate at another frequency. So you can see it here, the series resonant frequency and shunt resonant frequency, which are sometimes far apart. So then there is a kind of a stop band, or especially for the people who have started using for leaky wave antenna applications, they found that there is a break at that point. Okay, so the frequency scanning is not possible at these between these two frequencies. Okay, so it stands still at that particular over the range of frequency, and then again the scanning moves. Okay, so this kind of a structure is called unbalanced structures, and then you have to make a balance. How to make a balance in the sense means that you have to go for making these two resonant frequencies to be as close as possible. Okay. We can say just theoretically, and then keep the values, keep on changing it. That's what most of the students do it, right? Just randomly changing the values and then bring down to the same value. But one thing always one should remember, whoever is doing some research on this balanced CR-led structure, the first thing is the fabrication tolerance. Okay, this is not just randomly changing and then getting some results, theoretical results, which make it balanced, and then you are able to make the wide band of operations from this frequency to this frequency, F1 to F2. If we cannot realize these capacitance and these inductances by real fabrication limitations or some constraints of the dimensional tolerance, then no point. So always, whenever the research community has been doing, whoever is doing on the simulation studies, keep always that constraint, that fabrication tolerance is always kept, and then try to vary that post-processing, the parametric variations within that range. Okay, that's always my advice to most of my research students. Otherwise, they keep varying randomly here and there, and then just try to get some results, but it's just not possible to fabricate and then make it realize in a more applications. Okay. Okay, so let me come down. I don't know how much time I have. Let me share some of our works. This is my students' work, and as well as Dr. Nazim's contributions also here. This is the way we wanted to make it, because the CRLH unit cell, you can see it here. It's we try to make it at 2.45 gigahertz or close to 2.5 gigahertz, where it is ISM band, and then we can extract the all these Wi-Fi routers and then ISM signals. Okay. So the first task is to make it a balance, as I mentioned earlier, and then with the constraints of the fabrication tolerance, first the ADS simulation tool has been used here. To find out what are the typical values of these elements. So it has been extracted on this. You can see the LR value, the right-handed inductance 6.6 nanohenries, and then all this 1 nanohenries, and then the shunt capacitance is slightly larger. Okay, it's 2.5 picofarad compared to the series capacitance, which is in the order of femto or farads. Okay, so normally the CRLS structures, we will have a few cells. Okay, so this is a zeroth order resonance where beta equal to 0, right? So this is a zeroth order resonance, and when you try to see the parameters of this equivalent circuit for a unit cell or a kind of array of cells or periodical cells, you may observe that you have multiple resonances of the higher order. Okay, this is n equal to 0. Okay, you have n equal to -1, -2, or n is equal to 1 and 2. Then other resonances are beyond certain other higher order resonances are very weak. You can see around 5 resonances with open circuit terminations. Okay, this is the match flow terminations where it's getting perfectly matched. You can see that S11 is getting matched at 2.45 gigahertz, and you can see the resonances. This is at n equal to 0. This is -1, -2, and this is n is equal to 1 and 2 resonances. And other resonances are becoming so weak within this range. Okay, because it's going out of the passband ranges. Okay, but if you try to connect this with the open circuit, instead of match load, if you make it an open circuit termination, the signal gets reflected at 2.45, right? Because the reflection coefficient is getting maximized. You could see 2.45. So you could operate at the dual band operations at around this. Okay, you could because some of the modes are getting merged here. Okay, so this is the thing. Basically, we exploited it, making a open circuit termination or open circuited shunt elements at this point. So one could realize dual band of operations, but then the frequency could be tuned to the desired bands. Okay. Yeah, this is the way the pi model has been used here. This is the interdigitated one. Okay, one could make it just simple the open gap capacitance, but you may not get the enough inductance. Okay, so there are various canonical expressions that are available to estimate the dimensions first. Okay, which are available in most of the papers. Okay, or you could so this work has been already published in IEEE Antenna magazine in the recent issues, the June issue. So you could go there and then get the references and then start using those. I think expressions are available in the paper itself. So the canonical expressions could be used in designing the first approximate dimensions and then put it on the ADS or CST Micro Studio to get the more realistic dimensions or more appropriate and optimum dimensions. Okay, so these interdigitated capacitors, the finger length and then the gap between or the width of the fingers and then gap has to be decided. This is where your fabrication tolerance has to be brought in. Okay, you cannot just randomly change it. Okay, and the dimensions are given here. Okay, and these are the inductances. Okay, this is a series capacitance which you have introduced. Okay, and these are the shunt inductances. Okay, and the shunt inductance doesn't mean that you need to really make a wire hole down to the. It's a microstrip version, so down to the ground. Okay, here we made it wire hole free, so that a long loop of this the spiral wound can contribute to the desired inductance which you have calculated here. Okay, for the LL, and then you need to have a large capacitance. Okay, so that's this long length, and as well as the open circuited one provides a very high capacitance, so which is able to provide enough the capacitance for our balanced structure. Okay, and if you want to really calculate the dispersion behavior or more refined dimensions of or refined values of all these element values, you could use this also. You can you just through the CST Micro Studio or whatever simulation tool you are using it, get the S parameters. From the S parameters, convert into admittance parameter, impedance and admittance parameter, and you could use this expression and to get the element values. Okay, just be careful about it. This has been taken from Tatsuhito book. Okay, there are some typo errors. I'm not sure whether it has been corrected here or not. Yeah, you can check it. Okay. Because my student he identified some typo errors in his book, and I also convey to Tatsuhito because we have been meeting frequently at many places. It's one of my good friends also. That's why I've been using his work also for for all our investigations. Okay. Okay, so this is the structure we have come out. Just a 3-layer, 3 cells model. It's a pi model, which is this is the interdigitated capacitors with our inductor here. Okay, and it's a second stage. This one. Yeah, we just reversed it to the top so that we can save the space layout space. This side, okay, the inductances, and then for this one, this acts as the left hand side, and this acts as the right hand side. I mean, to have a kind of a symmetric one. Okay. So first we have done this, and then we try to vary some kind of a parametric variations. We also did. So by doing that, by varying all these values, we could merge some of the resonances, the 5 resonances which you have seen it earlier, could merge some of the resonance, like a zeroth order resonance and first order resonances coming very closer. So that could make it a slightly wider band, one band of operations. And then the first and second mode of resonance also could be brought in, get merged, and then can act as another potential band. Okay. And then we were not having a sufficient inductances from this. Maybe making a wire hole could solve the problem, but our interest is to avoid a wire hole. So by creating a slot underneath on the ground plane, which enhance inductance which enhance the capacitance at this open end chip. Okay, and then provided a large capacitance for the design circuits. Yeah, the first thing is we did the fabrication on the antenna part, and then individually tested it whether it is operating at a multi-band or not. So this is the fabricated structure. This is on R04003C substrate with the dielectric constant of 3.38 and then the thickness of around 0.79 or 0.8 mm thick. Okay. So first tested it. This is the back, the bottom view, which are slit. I mean the ground slots to enhance the capacitance, and you could see here it is resonating at a multi-band. You get 2.5, and then these are the higher order resonances. Okay. And the measured and simulated results are shown there. Okay, now coming to the rectification part. Okay, this is the antenna part. Then rectification has to be done, and of course the matching also to be done. I'll come down to the one which is followed by this. So we use the Schottky barrier diode, SM763 diode, Schottky barrier diode, and this is to match the input impedance to compensate the reactive part is 820 nanofarads for both diodes has been used to get better conversion efficiency. Okay. Yeah. Then the matching circuit will be done between the antenna and the load, or between the voltage doubler, or between the voltage, I mean the crystal detector. Okay. So we have used the quarter wavelength at the both bands, the matched at 2 bands, and then again we use the CRLH concept to introduce the phase shifts of typically 90 degrees, or the desired phase shifts could be uptime. The expressions are available in the paper. One could refer it because the short time, I don't want to spend much time on the explaining those mathematics there. Okay. So we got the desired phase shifts, and then this is the finally from the antenna, the width of the microstrip line has been designed with a slightly wider one to get the proper matching with the characteristic impedance of Z0 of 50 ohms, and then the electrical length, the phase shift has been introduced by the by this CRLH phase shifters. Okay, the pi model here. Okay, then this one goes to the voltage doubler. Yeah, so you can see the complete the entire network. Okay, so this is from the antenna, and this is the microstrip line which is being used, and then this is the CRLH. Sorry, this is at the both sides. This is at the both sides your the phase shifters. Okay, or the microstrip line one. This is the phase shifters. Okay. Then this one goes to the detectors, the peak detectors or the envelope detectors. Okay. So this is the measurements. You could see here it's a simulated, and then the measured results are seen there. It is operating at 2.45 and 3.75 gigahertz. Okay. Yeah, that's it's getting well matched with the simulated and measured, and then we were able to get a good amount of power. Okay. Yeah, this is the entire fabricated or integrated structures. Yeah, this is the antenna which I mentioned earlier, the CRLH zeroth order resonator antenna. Okay, the dual band antenna, which you could see that it's operating at 2.45 gigahertz and 3.75 gigahertz. Okay, then followed by the dual band matching circuits. Okay, dual band matching circuit. This is the microstrip line. These two are the microstrip line, which I shown it earlier there. And then these are some of the lumped components we have used for the CRLH phase shifting. Okay, and then the voltage doubler. Okay, the 2 diodes are kept it here. Okay, voltage doubler. Okay, we use 2 diodes with a capacitance here. This is the capacitance used 820 nanofarad, which is being used for the matching purpose. After that, this is delivered to the load. Okay. So this is roughly 8 centimeters length. And yeah, we could flip it. We could make it in the other way. We can make a flip technology so that we can make it even much more compact. Okay, since it is a prototype, a demonstration has been made, so we didn't really make it flip. And the commercial developers, one could even skews the layout and then bring this to the other side or a next layer so that you can make it much compact on the size. Okay. Yeah, this is the experimental one, which was done at the Institute for Infocom Research. The network analyzer there to provide the energy from the to simulate the transmitting antenna, whereas the horn antenna with a 9 dB, I think 9 dB gain, standard horn antenna. The distance we kept is around 60 because this we extended around, I remember it's around 10 milliwatts, maximum 10 milliwatts. Yeah, 10 dBm. Yeah, 10 dBm, around up to 10 dBm we have gone for it. Some results are up to 15 dBm, but 10 dBm itself, the efficiency has gone down. So maximum up to 10 milliwatts we went, and then the energy was getting decayed very sharply. So with around 65 centimeters, we have shown it because this network analyzer can go up to maximum 20 dBm or I think 15 dBm. Okay. So then this is the rectangular part, which the previous structure. Okay, this we kept it. And this, of course, this 60 centimeters is in the far field range for this antenna, this frequency. Okay, and this is to measure the voltage levels, which was coming out from this rectangular part or the load. Okay. And if you see the efficiency by varying the input power here, we varied from very low power, minus 10 dBm to plus 10 dBm. We could see that this is the estimated or the simulated conditions, and then the measured one. There is some differences are coming, of course, with the simulated and measured variations on the efficiency. That's basically due to the diode. Okay. And also some of the pads which were used. You could see that it's all in-house made. Nothing is commercially sent out, so it's all in-house made. So there are always some issues, but one could really improve it, and when you properly trained technicians make it, okay, or send it out for a proper professional fabrication. Okay. Yeah, so you could see that the efficiency is becoming maximum and then brought down, bringing down the efficiency lower. That's because of the reason which I mentioned, that the diode is a nonlinear device where it generates intermodulation harmonics, and which or mixing with some of the spurious harmonics which are created by this nonlinearity, and the saturation also contributes towards the reduction in the efficiency. So there is somewhere the maximum or optimum input on this could give a better efficiency on this. Okay. And also we have done the harvested power. We could see that with the varying power, which is the predicted the power using the Friis transmission formula, and then multiplying with the conversion efficiency, RF to DC conversion efficiency. You have to multiply it, typically 45 to 50% conversion efficiency. When you do that, you get predicted behavior over the transmitted power. Okay, so that's the harvested power or received power. But the measured values also just closely following it. But some of the insertion loss we didn't take into account. The last factor is not properly characterized here, but it's closely following the trend. Okay, then the patterns have been measured, because the another challenge is, rather than a constraint, is omnidirectional presence, because the energy may be coming from any direction. So your antenna should be able to capture from any direction, just like your mobile phones. Okay, so the XZ plane means on this direction. You could see them. Let me show the XZ plane. Where it is shown. Yeah, so this is the direction. XZ plane is the transverse, and then the YZ is on this direction. The XY is on the. So all three-dimensional the pattern measurements have been taken to show that the energy is omnidirectional. Yeah, so this is on the XZ plane. This is at first band, 2.45 gigahertz. This is on the YZ plane. Okay, and then this is on the XY plane. Okay, it's on the planar area. Okay, and then the second band, 3.75 gigahertz XZ plane, and then the YZ plane, and then the planar plane of YZ plane. Okay, so both the simulated measures were done. These patterns have been also measured at the chamber, anechoic chambers at the Institute for Infocom Research. Okay. 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 So another 5 more minutes. Maybe I'll try to briefly tell about the energy harvesting using metasurfaces. Okay. The metasurfaces are also getting popular recent days. Metasurface is nothing but artificially generated the two-dimensional metamaterial. The metamaterial we have seen is it's a kind of a one-dimensional. It could be made as a two-dimensional also. For example, one could realize the SRR structure, especially the terahertz. People started using the SRR structure to realize some filtering applications that are terahertz. Okay, the metamaterial SRR at terahertz frequencies. So, energy harvesting system based on a metamaterial splitting resonator structure was done by from lower RF to microwave, millimeter wave, or even at terahertz bands, as I mentioned now. Okay, a 2.5 also some group has done on that. The proposed harvester consists of I think this was done by Ermai, and then this group with the references shown at the bottom of the slide. Okay, so they used around 8x8 resonators to function. Basically, it's a metasurface is a very simple way of telling is it's a two-dimensional metamaterial. Okay, the energy is with the energy incident on the surface, it's able to create a kind of a abrupt phase shifts, and then chromatic dispersion is also possible. So that's where that's the thing could be exploited. And then another important thing is it's a sub-wavelength. You don't need to really go for a kind of the cavity back to mean like quarter wavelength, the back reflections to enhance your array antennas. So this is one way of making metasurface. You can see on the right hand side, this is the SRR structure, the metasurfaces, over which the overlaid the patch antennas, which is getting excited by the coaxial feeds here. Okay, and then the different phase shifts which are created by these metasurfaces. Okay, at which was done at 30-degree phase shifts, 45-degree phase shifts, or 60-degree phase shifts, so at different frequencies. This was done by that group. You could see that paper in APL in 2012. Okay, and each resonator gathers the power from the ambient environmental energy and delivers all the collected power from all resonators into one output terminal port. So you had to generate a corporate feed network or a capture network or collection networks to get a RF combining network to get the maximum energy. Okay, so then the total delivered AC power is converted into DC current using a single RF rectifying circuit to power a load. Okay, that's the way it is done, and the efficiency is quite. It is by that group. I think the efficiency was shown around 70% at certain the phase shift created. Okay. Okay, so yeah, this is done by the another group where you could see that the RF combining network. Okay, so this is yeah, this is the structure, the metasurface structures with the SRR configured like this with a stub. Okay, and then below that it's a capturing network. Okay, the energy capture and single RF one, and then which is fed to your rectification unit, and then just show the LEDs the output LED load, where you could see that the LED is getting powered up based on the power received. Okay, so the AC power is simulated, and then this is very recent one, not recent one. It's a few years back. It's around 2016. Yeah, it's published in AAP Advances. Okay, and here also you could see the input AC power. It's showing at a maximum power efficiency at a certain input. Here, they're all based on the diodes nonlinearity behavior. Okay. So depending on the incident angles, your power capturing could vary, but the harvester can go with some kind of a super cells with alternating wires between neighboring cells, that could be connected by a feed network as shown in this one. And also this introduces some more insertion laws also. So you have to group the cells within the subcells architecture. Okay. And the subcells can be connected by a feed network as shown in this figure. And then the feed network combined with the supercell configuration metamaterial using an additional layer in the bottom could lead to, but that then becomes a kind of multiple layers. Okay. So there are various works. I think you may find this paper has been published by myself and Dr. Nazimuddin, mostly supported by our neighboring country, Malaysian. There is one research student and another the faculty who was my former student also. I did some work on that. So this paper is recently has come in IEEE Access, so you can refer it. That is more review on all the meta surfaces for RF energy harvesting. Okay. Actually, I wanted to cover more, so the time is getting 90 minutes. I'm spilling over the next person's time, because here is already almost close to 10:30 in Singapore, so maybe it's in India, it should be okay. Anyway, what I've done basically is the basic concepts of the energy harvesting, a brief overview of what is energy harvesting and how a metamaterial could be used, so the basic concepts on the metamaterials and how to realize the composite right left-handed transmission line and making composite right left-handed transmission as a zeroth order resonance, and how to merge the higher order resonances into the zeroth order resonance to make a wide band of operations, and metamaterial concepts have been discussed in this short 90 minutes presentation. And how to enhance the energy harvesting also is done by using a meta surfaces. And the basic principles have been discussed very briefly due to the short limitations, but short time limitations. But hopefully you can go through the IEEE Access paper to get a complete picture of the meta surface. Okay, I'm coming to the end. Now it's open to floor. Dr. Taimo?
Thank you, Professor Alphonse, for your wonderful talk. How you have started from basic fundamentals of energy harvesting, then enter into the step-by-step advanced version, finally concluded on meta-surface-based RF energy harvesting system. As per our time constraint, because several queries are there in that chat box of YouTube, but it will be very difficult for us to I request you to go to that one, but one or two query I can share on the behalf of that particular participants. One participant has put a query whether silicon diode IN4007 supports 2.4 gigahertz energy harvester, or in simply, is it possible to use IN4007 diode as an rectifier circuit for RF energy harvesting application?
Yeah, one has to need I think you need to find out how much the conversion efficiency at that frequency. So you need to use a SPICE model first. Basically the data sheet of the IN40 can be put into a SPICE model. Let's see how much the conversion efficiency. So one could decide on that. Yeah.
Yes. Then another query which I am feeling that it is relevant to the talk is that how metamaterial based absorber can be used for RF energy harvesting application.
Yeah, it's all metamaterial absorbers, right? So and the kind of periodic structures, the meta surfaces is being basically started for absorbing purpose only. Okay. And as much of energy you absorb, you get a more amount of it. But it's basically a metamaterial absorber activity.
Okay. Thank you, Professor Alphonse.
Yeah.
For this wonderful session as the opener of this workshop, that will be remembered as the opener of this workshop. Okay. And several doubts are there, but it is not possible to discuss right now because of time constraint. Later on, through some other platform, we'll discuss with you in detail.
Sure.
With this, I again thank you very much for sparing times with us for this talk. Now, I would like to invite our second speaker, Dr. Brinda Bhaumik, Associate Professor, National Institute of Technology, Silchar, India, for delivering her talk on tunnel FET-based rectifier circuits for RF energy harvesting application. Professor Brinda Bhaumik, are you there online?
Yeah, I am online.
Okay, ma'am. Okay, ma'am.
Yeah.
Start your talk.
Okay, but here it is showing Alphonse is presenting in my
So
device.
Alphonse, you please like leave that presenting session so that the second speaker will come into the screen. Professor Alphonse, are you hearing me? Brinda, ma'am, I think Professor Alphonse has already left the meeting.
Left the meeting, but still it is showing Alphonse is presenting. Then, and in my PC, in my laptop also. Okay. Now I got the option.
Okay. Now you please start the session.
Yeah. First of all, very good afternoon, good morning, good night to all respected distinguished speakers and my dear participants. I want to congratulate PI Dr. Taimur Khan and his team for conducting Indo-Canadian SPARC workshop, RF energy harvesting system. I also want to thank NIT Silchar, Delhi Technological University and Queen's University, Kingston, Canada, for organizing the workshop in this COVID pandemic situation. And I also wish a grand success of the workshop and hope that this will increase the knowledge of our students as well as research scholars, and they will learn many things from it. Okay. So today I will present tunnel FET based rectifier circuit for RF energy harvesting applications. So what is actually RF energy harvesting? RF energy harvesting is the conversion of RF ambient input power present in the environment to electrical energy for use in powering autonomous electronic devices and circuits. But the major concern is the low DC level of the RF rectifier, or due to the low power of the RF and ambient input and the reduced power conversion efficiency. So in my discussion, I will try to explain you an emerging device that will be replaced the diode, such that we can get better sensitivity as well as better power conversion efficiency. Now my outline of presentation is given. First, introduction, then challenges, key performance parameter of the rectifier, then motivation for emerging device, band-to-band tunneling, various emerging tunnel FET structures, investigation of linearity parameters, noise in tunnel FET, then block diagram of rectifier and various rectifier topologies. So in introduction, what are the I want to say that what are the applications of RF frequency powered energy harvesting systems? There are various applications like health monitoring, biosignal acquisition, battery-less data transceivers. So for that, we need a rectifier with high sensitivity, high power conversion efficiency. Low power sensor technology advancements and circuit design techniques have offered many applications powered by the RF signals in the ultra frequency band. And power consumptions in these systems ranges from few microwatts to milliwatts. The block diagram of RF energy harvesting system is shown in this figure. Now, energy harvesting system consisting of impedance matching, as Alphonse sir has already explained, rectifier, which is converting ambient RF input to DC. Then, according to the desired application, some voltage booster is required, which is required for conversion of DC to DC. DC power which we are getting is low level, we want to convert it to a high level, and a voltage regulator. So in my discussion, I will give stress on the rectifier of which is required to convert RF to DC. And in this block, the signal conditioning, data processing, sensors, these are also shown, RF transmitter, oscillators. So complete RF powered energy harvesting system is shown in the block diagram. So many rectifiers were designed based on CMOS based circuit. Now, what are the disadvantages we'll get? So many diode connected charge pump, the Schottky based, diode based, two terminal based CMOS rectifier designs had been proposed due to their desired process compatibility with the CMOS circuits. But these designs suffer from the efficiency loss induced by a large threshold voltage, or we can say turn on voltage. Has the maximum power efficiency, that is PC, is relatively small. And rectifier operation requires the RF signal voltage amplitude above the turn on voltage of a transistor or diode. In the sub-threshold region, means a device operates in off state, then sub-threshold region, then in the on state. So in the sub-threshold regime, we will find that a large on-state resistance is existing due to the drive current reduction. And this on-state resistance is responsible for increased voltage drop on the rectifier. And this leads to a high resistive power loss and reduced output DC voltage, as well as power conversion efficiency. Therefore, we must go for a device that must have small turn-on voltage, and it should provide us high sensitivity rectifier. For designing a rectifier with high sensitivity and high PC to allow long-range communication with more computational capability becomes challenging. Now, PC analysis for various rectifier design is shown in the figure. The input RF power, the range of ambient input RF power is lying up to -30 dBm. Now, in this range, we can see the colored portion in the figure. The limited PC will obtain. The PC is very less, which is around 20%. Therefore, we need to improve the power conversion efficiency. These are all reported data from the CMOS rectifier designs. So the PC below -30 dBm RF input is less than 20%. Hence, the design of a high sensitivity, high PC RF rectifier is critical to achieve longer operation range and more functionality for RF powered application. Next is the key performance parameter of RF rectifier design. The key performance parameters are DC output power, DC output voltage, and the power conversion efficiency. So the DC output power is expressed as twice of RMS value of the input voltage minus the drop, V drop. V drop is the voltage drop across the rectifier circuit. And power conversion efficiency is nothing but power output power by the input power, where input power is nothing but it has loss component. So various loss components are due to leakage, reverse conduction, switching loss, charge redistribute, and resistive loss. So what is P leakage? P leakage is due to the transistor off-state leakage. Switching loss is due to the average capacitive switching loss. The reverse loss due to reverse conduction, and P redistribute. P is due to the charge redistribute between coupling capacitors and transistor network. P resistive is a loss due to the non-zero on-state channel resistance. So all these factors are responsible for reducing the power conversion efficiency. So our aim is to reduce all those factors. Now, motivation for selection of emerging device. Why you go for an emerging device? Means the device which will provide us reduced losses. A device with steep subthreshold slope, high on current at reduced power supply voltage, high on-off current ratio, unidirectional conduction can be explored to reduce the power losses. So next we consider the TFET technology for analog application. TFET has emerged as a promising candidate to mitigate the supply scaling challenge. How it will reduce that effect? Because in case of MOSFET, when you reduce the supply, when you scale the supply voltage, our threshold voltage is also simultaneously scaling down. And due to that, what will happen? The off current of the CMOS device is increasing. So this is an undesirable effect. But in case of TFET, even if we reduce the supply voltage, the off current is not increasing. So that relationship is not possible, means not applicable to tunnel FET. TFET means a tunnel FET, where the principle of operation depends on the band-to-band tunneling. So what is band-to-band tunneling? Band-to-band tunneling is nothing but the injection of carriers from one band to another band. So this mechanism is used in a reversed biased gated PIN diode, where you will get, see, MOS structure is a symmetric structure, but TFET is a asymmetric structure, and its operation is controlled by the field effect. The field effect, similar to the MOS, since it is a FET, tunnel FET is also a field effect transistor. The tunneling current is controlled by the field effect. This is the basic structure of tunnel FET. So tunnel FET works on the Zener tunneling. So what is Zener tunneling? We have studied in basic semiconductors. The devices in undergraduate level actually will study this thing, Zener tunneling. Zener tunneling occurs in case of highly doped junctions, where the tunnel width is very small. Then Zener tunneling can take place. And a TFET can operate in both mode. It can operate in P mode as well as it can operate in N channel mode. So if we consider the N channel mode, then what are the polarities will apply? In this structure, 3 terminals are shown. One is the gate voltage, source voltage, another is the drain voltage. Now, when you want to operate the TFET in N-channel mode, will apply higher potential to the gate with respect to the source and higher potential to the drain with respect to the source, such that both the junctions, there are 2 junctions, are reversed biased. Next, the energy band diagram is shown in the figure. Now, VDS, this diagram is plotted for drain to source voltage 0.5 volt, and obviously the diagram is plotted for N mode operation of the TFET. The vertical axis shows the energy which is measured in electron volt, and horizontal axis shows the position along the channel. Means left side is source, middle is channel, and right side is the drain. Now there are 2 graphs. One is red colored, another is the black colored. The red one shows VGS, gate to source voltage 1 volt, and the black one shows gate to source voltage 0 volt. Now, when you are applying 0 volt, see, the location of conduction band and valence band is shown in the figure. The large gap is observed when you consider 0 volt VGS, means gate to source voltage. But when you apply positive gate voltage, then what will happen? The energy bands are pushing downward by the application of positive gate voltage with respect to the source. And due to that, the tunnel width is reducing. Therefore, what will happen? The electrons which are existing in the valence band of the source, they can tunnel through the barrier and they can reach to the conduction band of the channel. And in case of TFET, a very high electric field is existing at the source channel junction. Now, due to that high electric field, the carrier velocity is very high near the source channel junction, unlike the MOSFET. And another thing is that when the carriers are entering in the channel, they are getting reduced electric field. And due to that, the carrier velocities are reducing. And in order to enhance those carrier velocities, sometimes compositional semiconductors are used, such that the quasi-electric field in the channel can be increased. Now, this is the ITRS data shown in the figure for the year 2013 to 2028. Now we can see from this figure, for tunnel FET, research is still required and its development is underway because of the fact that conventional tunnel FET, which I have shown here, it has lots of disadvantages. So I am coming in the next slides. Now I am showing the ITRS targets. So ITRS target in 2013 to 2010 to 2025, it is shown in the figure. The high performance devices are shown by the black lines, and the TFET performance is shown by the red dots. So off current, first graph is showing the off current, and second graph is showing the saturated current, means on current, for against the years measured from 2010 and projected up to 2025. Now we can see that the off current level of TFET is still lesser than the high performance. So off current level is good. But when you see the saturated current, or you can say the on current, the high performance devices have more current And group 3,5 material as well as germanium material based devices are also having good, better on current or saturated current. But TFET, which is shown by the red marks, red dotted lines, still lower than this. So in order to drive the circuits using TFET, we need more research. We want to improve the device current, tunnel fan device current. So here, the energy band diagram for the MOSFET as well as for the TFET is shown in the figure. MOSFET, thermionic emission takes place where the carriers are overcoming the barriers. But in case of TFET, the carriers are tunneling through the barrier via band-to-band tunneling process. So, unlike MOSFET, the gate-controlled tunneling window in TFETs is able to effectively filter the high energy carriers in the energy band and hence leads to sub 60 millivolt per decade steep slope at room temperature. For MOSFET, there is a limitation in sub threshold swing. Because the slope cannot be much steeper. But in case of tunnel FET, since the operation is not based on direct drift diffusion, so that limitation of sub-threshold swing is not applicable to the tunnel FET. In order to achieve the projected energy efficiency benefits, a desired tunneling current at the device on state, a high on-off current ratio, and an average steep SS means subthreshold swing over a few decades of current change are the key design factors for the TFETs. So here, just now I told the high energy tails. See the last in this slide. The gate-controlled tunneling window in TFETs is able to effectively filter the high-energy carriers. So, from this diagram, you can see there are two diagrams. A is for MOSFET and B is for TFET. In TFET, the high-energy part of the source distribution is cut off by the band gap region, and it leads to sub 60 millivolt per decade sub-threshold swing. And another factor is that phonon-assisted tunneling becomes important under these conditions. Why this is there? I am discussing it. So I'll discuss in this slide the basic of band-to-band tunneling. For band-to-band tunneling to occur, an electron in the valence band of the semiconductor tunnels across the band gap to the conduction band without the assistance of traps. Means no help of trap is taken. The band gap acts as the potential barrier that the particle tunnels across. An electron, obviously we're discussing N-mode operation. An electron travels from the valence band to the conduction band without the absorption or emission of photon in the direct tunneling process. A tunneling particle is nothing but an electron acquires a change in momentum by absorbing or emitting a phonon in indirect tunneling process. So we can see the diagram next, that in case of here the full band structure of unstraight silicon is shown in the figure. It's gamma direct. Here it is gamma centered energy band gap is shown in the figure. The gamma centered energy band gap is 3.4 electron volt, which is much greater than the indirect band gap, which is 1.1 electron volt for silicon. Therefore, tunneling, even if the tunneling path is larger, even though phonon provides momentum and tunneling will takes place via the indirect tunneling process in case of silicon. And the energy and perpendicular momentum are conserved. So this already I have discussed. Applying positive gate voltage, we can push the energy band, and this allows the electron in the valence band of the source to tunnel through the barrier, and tunnel FETs provide sub 60 millivolt per decade subthreshold swing. Now, what is current? What is the band-to-band tunneling current? The band-to-band tunneling current is proportional to the tunneling probability. The tunneling probability is calculated by Winzel-Kramer-Brillouin approximation. In this approximation, it has been considered that the potential function is linear and it is a slow function of distance. So we can see that the tunneling probability, which is given by T, is proportional to exponential of negative factors 4 into lambda, where lambda is the screening tunneling length. M star is the effective carrier mass. Eg is the band gap of the semiconductor, and del phi is the major factor, which is the energy range over which tunneling takes place. So what is the del factor? Here, the energy band diagram for P mode operation means tunnel FET in P mode operation is shown in the figure. Here the source, here the source is considered as N-type, N+ type, highly doped N-type semiconductor, and drain is P-type semiconductor. Now, when you consider the P mode tunnel FET, we will give negative gate to source voltage. Since we are applying negative gate to source voltage, therefore the energy bands are pulling upward, and conduction of carrier takes place at the source channel junction, which is nothing but the holes are tunneling from the source conduction band to the valence band of the channel. And del phi is shown in the figure, which is discussed in the last slide, that tunneling probability is also a function of del phi. So del phi is nothing but it is the energy range up to which tunneling takes place. So del phi is shown in the figure, which is, we can say that the difference of energy level in the valence band of the channel to the conduction band of the source. And obviously, source should be highly doped such that the tunnel width should be lesser. So this is the band-to-band generation rate. This is already calculated by Keynes in a paper. So these are the various factors A and B, depends on the parameters of the devices. E is the electric field at the tunnel junction, and Eg is the energy band gap at the tunnel junction. So band gap is also an important factor at the tunnel junction. So conventional TFET has many disadvantages. So from ITRS data, we have seen that the on current is still reduced than high performance devices, as well as the higher threshold voltage is observed in tunnel FET, and since the on current is less, the ion of current ratio is also low, and switching speed of the tunnel FET is also slower than the MOSFET. So why we are going for tunnel FET? Because tunnel FET has one of the advantage that its off current and threshold voltages are not, if we increase the threshold if we decrease the threshold voltage, the off current is not increasing. So we are getting better off current as well as better subthreshold swing. So our research is based on the modification of tunnel FET structure by introducing source engineering, or by considering channel engineering, or by using gate engineering, such that we can get better on current, so that you can improve ion-off ratio, and we can improve its Miller capacitance. So what is the Miller capacitance? Miller capacitance, if we consider the common source configuration of the TFET, then Miller capacitance is nothing but the capacitance connected between gate to drain. So this capacitance is larger in case of tunnel FET. So in order to reduce that capacitance, we have to go for many optimizations. So various tunnel FET device structures has been proposed, and still people are doing research so that its parameters, electrical parameters as well as analog RF performance parameters can be improved. So the first structure is shown, which is nothing but lateral and vertical tunnel FET structure. Here the red marks are showing the electron tunneling, and blue marks are showing the electron drift diffusion. Now vertical tunneling means lateral tunneling means tunneling takes place parallel to the gate oxide and silicon interface, and perpendicular tunneling means a tunneling takes place between gate oxide and semiconductor, which is perpendicular to that interface of oxide and silicon, or oxide or any other material. Now next structure is the 2D structure. These are all simulated structure in TCAD. Santora's TCAD simulation is used to develop those structure. All the structures are still in research. Still we are doing research on the structures. In the structures we can see the gate is hetero. Hetero means it is a mixture of high K gate dielectric as well as low K gate dielectric. Hafnium dioxide is a high K gate dielectric, which is used to improve the control of the channel by the gate. When you scale the device, our drain starts controlling over the channel. So in order to improve that, HFO2 is used and SiO2 is used near the drain side, so that no tunneling will take place at the drain junction. Means the off current or current due to MB polarity should be less. So if we see this structure, in this structure, the buried oxide is used, and buried oxide is raised in the drain side. Now, figure 12 shows the comparison of raised buried oxide in drain, raised buried oxide in channel, and raised buried oxide in source. Out of this, we are getting the best structure for the raised buried oxide in drain, because the surface roughness scattering in the source and the channel of raised buried oxide structure increases as compared with the drain region. Why this occurs? Because of the fact that the peak electron concentration is located at some distance from the raised box in the drain, and accordingly the peak electron concentration occurs at the source tunneling junction. So in this figure you can see that peak electron concentration occurs in the source channel junction because tunneling takes place there, but the raised buried oxide should be far away from it. Hence, the overall mobility is not degraded, but the thickness of the drain side is reduced and off current is reduced, and therefore better I on-off ratio can be achieved in this structure. Next, comparison of high K gate only and the tunneling. The figure shows tunneling barrier width in the y-axis, in the vertical axis, and the gate voltage along the horizontal axis. Now, when you consider the last figure, we have considered HG TFET, means hetero gate TFET, and the blue line shows the high K only TFET. Now we can see if we use the HG TFET, HG means hetero gate TFET, then the tunneling barrier width is much lesser than the high K only TFET. So we always prefer the high K instead of high K only TFET. We prefer hetero gate TFET structures. Now, next, so in the first structure, we have seen the vertical tunneling. The last structure, we have seen the gate engineering as well as drain engineering. Now, in this structure, we'll see heterojunction structure, because our tunneling probability is proportional to the band gap, as well as the tunnel width is also an important factor. So, in order to modulate the tunnel junction barrier width as well as the tunnel width, we can use SIG material at the tunnel junction. By controlling the mole fraction of the germanium, we can control the tunneling of the carriers. So, the effect of germanium mole fraction is shown in the figure. Here, the drain current mole fraction we are varying, and drain current versus gate voltage is shown, and on current is also shown in the figure. Okay. So our time is very less. So I have made many slides. Many devices are there. You can see the structures only. Okay. The elaborate discussion is not possible, I think, because I have to discuss the rectified topology also, last topic. Okay, just see the structures, different structure. Another is the PN TFET, where what we have done, the gate is hetero gate. You can see HF42 is near the source channel junction, and near the drain channel junction, SiO2 gate dielectric is used, and N minus pocket is used at the tunneling junction. And N minus pocket is fully depleted, which reduces the tunneling width and creates local bell bending, and due to which very steep subthreshold slope is obtained. Next is the circular gate TFET structure. So this structure is actually published in IEEE transaction paper in 2016. So in this structure, the shape of the gate is circular. So we can see by controlling the radius of the structure, by radius of the gate, we can control the ambipolar current. So what is ambipolarity? When a negative voltage is applied to the gate, means say a TFET is working in N mode operation. So what type of voltage we are giving? We are giving positive gate voltage. But whenever we give slightly negative gate voltage, then what will happen? BTBT current starts also flowing, which is defined as the ambipolar current. The difference between the on and ambipolar state is the position where BTBT occurs. In ambipolar state, unwanted BTBT occurs between the channel and drain. This ambipolar behavior means that the TFET is turned on even when it is expected to be turned off by applying negative gate voltage, which limits the feasibility and applicability of the TFETs. So in this structure, you can see by controlling the gate drain underlap means when this structure, when you reduce the radius, then what will happen? Then gate drain underlap will be created. Means some part of the channel is not to be connected to the gate. So this gate drain underlap effect will reduce the ambipolarity. You can see the ambipolarity effect in minus gate to source voltage. When gate to source voltage is negative, the ambipolarity for 0 nanometer, 4 nanometer is more. But when you give 8 nanometer gate drain underlap, the ambipolarity is reduced. Now this is a basic fabrication process flow, which are not fabricated yet, but tentative process flow has been discussed. I'm not discussing elaborately, just I'm showing you. So the fabrication process flow is compatible with the CMOS process flow. Then we have various structures. Gate on source tunnel FET. Then we have the germanium source vertical TFET. Source is P plus germanium and I intrinsic silicon is a channel and N plus drain is shown in the figure. Here only vertical tunneling takes place. And this will improve the subthreshold swing very much. Below 20, this structure is also published in IEEE transaction on electron devices. And the subthreshold swing is even below 20 millivolt per decade. And this is optically gated tunnel FET structure. This optically gated tunnel FET structure is shown where source is consisting of, in the source, one germanium pocket is given, channel, drain, and gate is consisting of N plus silicon gate. So these are the various structures we are discussing so that we can improve the on current, we can improve the subthreshold swing, we can improve various RF analog performance parameters of the tunnel FET. Basic fabrication process flow of the device is given. So I am skipping few slides. RF circuit performance parameters I am not discussing in detail. There are various linearity parameters, distortion factors, and noise are also there. These are these all to be studied for better performance of a particular device. One of the factors is transconductance. Effect of transconductance is measured in presence of temperature, how it varies. And another is the transconductance frequency product. Then we have intrinsic delay. Delay depends on capacitance, supply voltage, and on current of the device. So how delay is varying with respect to the temperature is shown in the figure. Delay is more when you reduce the temperature. Then we have transconductance generation factors. These are the various parameters. Gain, transconductance, and frequency product. So all these linearity parameters are also there. I'm not discussing because time is short. So next we move to the noise part also I'm not discussing. I'm going to discuss now the design of RF rectifier. So why we are going for tunnel FET? Because we want to replace our device by the rectifier. Now equivalent circuit is shown in the figure. First part is antenna. Equivalent circuit of RF rectifier with impedance matching is shown. The first part is our antenna, then second part is impedance matching, then is a rectifier. So harvesting sufficient power from the RF signal is difficult because the voltage of the RF signal is in the range of approximately 200 millivolts. Supply voltage for circuits of the RFID tag is 1 volt. So power rectifier circuits may be used to increase the output DC voltage. Rectification is difficult when the incident power levels are very low. Therefore, most of the rectifiers have an unresponsive dead zone at low voltage amplitudes. So small turnover voltage is one of the most important factor of the rectifier design. Means the device which will be used in the rectifier should have small turnover voltage. This makes steep slope devices such as tunnel FET attractive for this application. So various topologies of the rectifier. First topology is a 2 transistor topology, which is based on diode rectifier. Conventional diode rectifier. During the negative half cycle, M1 is on and current flows from Vy to Vx via the load resistance. But in this case, the increase in leakage current is more due to the presence of static voltage bias at the transistor off state. Next is the 4 transistor topology. So 4 transistor topology is derived from the standard cross-coupled CMOS rectifier with dynamic threshold voltage cancellation technique. Here, the devices, all the devices are used are tunnel FET. During the, here in my research, I have used the circular gate tunnel FET structure. So during positive half cycle, you can see M to P and MP and N. N shows the N mode devices, N mode tunnel FET devices, and P, M to P and M for P shows they are showing the P mode devices. During the positive half cycle, M to P and M to P are turning on, and current is flowing through RL. And at that time, M1N and M4F P are off. And another topology is nothing but 4NT topology. Means 4NT topology is also derived from the 4 transistor topology, because in this topology, the P mode devices are replaced by the diode connected N mode devices. Means M2 and M4 are diode connected because of the fact that PTFET suffers from degraded subthreshold swing. To mitigate this, PTFET is replaced by diode connected NTFET, and reduced turn-on voltage of NTFET is also an additional advantage. Now we can see for circular gate TFET, the IDVG, the drain current versus gate to source voltage graph is plotted. We can see the black line is showing the circular gate for NTFET, and the red line is showing the circular gate for PTFET, circular gate structure for PTFET. Now we can see from here that in case of NTFET, the subthreshold swing is steeper, and even our ambipolar current is much lower, because at negative VGS, we are getting the ambipolar current for NTFET. But you can see for PTFET, the ambipolarity is measured from 0 volt to positive VGS, gate to source voltage, but the ambipolarity is also more. Therefore, what we are doing in 4NT topology, the P mode tunnel FETs are replaced by diode connected N mode TFETs. And these are the RF rectifier waveform. For the input voltage is shown in the figure, and current for M1 tunnel FET in 4T topology is shown. So what we have seen that when 0 to T2, so the time division is given 0 to T1, then T1 to T2, then T2 to T by capital T by 2, and to total time period T. Now 0 to T1 is the subthreshold region, T1 to T2 is the odd state, and T/2 to half of the time period is a subthreshold swing, subthreshold region, and the T/2 to capital T is the off state. In the subthreshold regime, what we will obtain that in the subthreshold regime, we will see that the current which is shown in the right for vertical axis in the right hand side, the current for the CG-TFET is more for subthreshold regime, slightly more. Why it is more? Because CG-TFET has reduced subthreshold swing and current is proportional to e to the power 1 by subthreshold swing. So if subthreshold swing reduces, then the current in the subthreshold current is increasing. But the measured current for the heterogate HJ-TFET means the heterogate TFET, heterojunction TFET. Heterojunction means in the source channel junction we are adding SIG layer. Heterojunction TFET, the on-state current means the region.
Hello. Hello. Dr. Brenda Bhumik. Hello. Hello. Dr. Brenda Bhumik. Hello. Hello. Dr. Brenda Bhumik. Hello. Hello. Dr. Brenda Bhumik.
क्या हो सर मैडम पहुंचिए ना मैडम पहुंच
बोल रहे हैं कि दो
You make announcement.
Hello. Hello, Dr. Brenda Bhumik. Are you there online?
Make some announcement. 2 minutes. You make announcement.
All the participants, please be connected. There is some internet issue, some network problem, I think, at the end of Dr. Brenda Bhumik. All the participants very easily connected. There is some internet issue, some network problem, I think.
Video of course require.
Hello, am I audible?
Yes, you are.
Okay, sir. Okay, sir. Now, Professor Brinda Bhaumik has completed her lectures. Our last speaker for this session is Professor Yahya Antar, sir. Before inviting you, it will be an honor and privilege to read your short biography available with me. Professor Antar received his BSc Honours degree in 1966 from Alexandria University, Alexandria, Egypt, and MSc and PhD degrees from the University of Manitoba, Canada in 1971 and 1975, respectively, all in electrical engineering. In 1977, he held a Government of Canada visiting fellowship at the Communication Research Center in Ottawa, Canada, and in May 1979, he joined the Division of Electrical Engineering at the National Research Council of Canada. In November 1987, he joined the Department of Electrical and Computer Engineering at the Royal Military College of Canada in Kingston, where he has held the position of professor since 1990s. And also, he has cross-appointed professor at Queen's University in Kingston, Canada. He has authored and co-authored about 250 journal papers, several books and book chapters, over 450 refereed conference papers, holds several patents, has chaired several national and international conferences, and has given plenary talks at many conferences of repute. He has supervised and co-supervised over 90 PhD and MSc theses at Royal Military College of Canada and at Queen's University, Canada, several of which have received the Governor General of Canada Gold Medal Awards, the Outstanding PhD Thesis of the Division of Applied Science, as well as many Best Paper Awards in major international symposia. He served as the chair of Canadian National Commission of RC 1990 to 2008, Commission B 1993 to 1999. Dr. Antar is a life fellow of the IEEE, a fellow of the Engineering Institute of Canada, a fellow of the Electromagnetic Academy, and a fellow of RC International Union of Radio Science. He serves as an associate editor of many IEEE and IET journals, as an IEEE APS distinguished lecturer. In May 2002, he was awarded a Tier 1 Canada Research Chair in Electromagnetic Engineering, which has been renewed in 2016. In 2003, he was awarded the Royal Military College of Canada Excellence in Research Prize and the RMMC Class of 1965 Teaching Excellence Award in 2012. He was elected by the RC Board as Vice President in August 2008 and in 2014, and to the IEEE APS ADCOM in 2009, and presently he is the President-elect of IEEE Antennas and Propagation Society for the year 2020. On January 31st, 2011, he was appointed member of the Canadian Defence Advisory Board of the Canadian Department of National Defence. In October 2012, he received the Queen's Diamond Jubilee Medal from the Governor General of Canada in recognition for his contribution to the Canada. He is the recipient of the 2014 IEEE Canada Fessenden Silver Medal for the groundbreaking contribution to electromagnetics and communication, and the 2015 IEEE Canada JM Hams Outstanding Engineering Education Award. In 2015, he received the Royal Military College of Canada Cowen Prize for Excellence in Research. He is the recipient of the IEEE Antenna and Propagation Society prestigious Chen Tu Tai Distinguished Educator Award for 2017. With this, I invite you, Professor Antar, to start your talk, please. Sir, you can start your talk.
Okay, can you see my presentation?
No, sir.
Okay, I'll try again.
Sir, on bottom side, there will be an option of present. On bottom side of your screen, there is an option of present. You click that one.
Yeah. Can you see it now or no?
No, sir. Still it is not visible.
Okay, well, I tried that yesterday, so I'll...
Stop. Okay. Sir, you try now.
Yeah, I'm trying. It's not coming along. So
Sir,
did you let me in?
On bottom right hand side, there will be an option of present now. You need to click on that one. On bottom right side.
That's what I did. And it says your window. So I'm going for a window. And it's... So, do you see it now?
Sir, now it is coming, I think.
Okay.
But
I can see it now. So, am I audible as well?
Yes, you are audible.
Okay, well, thank you very much, Taimur. Good afternoon or good evening now, everybody. Thanks again for arranging that. And as I said earlier in the... and can you hear me or not?
Yes, we can hear you.
Yes. As I said earlier in the inauguration, it's really a fantastic opportunity for us to meet and so on. So I will, and thanks Taimur, by the way, for taking quite a bit of my time in talking about me. That's really very humbling. So that will make me speak less, a lot of time. As you can see from the title of...
Sir, sorry for interrupting in between. Sir, your PPTs are not visible.
My
PPTs are not visible to us.
My what?
Your PPTs are not visible to us.
So you don't see the presentation?
No. We are not seeing your presentation.
Okay. I had it before, so I thought you've seen it. So I'll try again. So you see it now?
Excuse me. Sir, you first open your presentation.
Okay, that's what I did.
Okay, Then you click the present now option.
Okay. It says you are presenting, so I am presenting now.
Yes, you are presenting.
Sorry?
You don't need to minimize this.
So I'll stop.
Okay.
And
Yeah.
One solution would be you can ask his PPT to send it to you, and then you can
Okay.
share this.
Sir, one thing we can do, is it possible to mail me your presentation so that I can scroll your presentation here and you can talk on the PPTs from that side? Is it convenient for you?
I don't know if I can, it's a bit big, so.
Okay.
I think I sent you a copy. Jawad, you have a copy of it. Can you mail it to Timur? Minimize. You see it now?
No.
I'm not having too much luck here. So it says I am presenting now. So do you see it now? You see it now?
Yes, now it is visible, sir.
Okay, I'll start now by again, thank you and thanks everybody for that. As you can see in the title, it's dealing with specific dielectric resonator for RF energy. I will take this opportunity to, and the fact that we have, so many audience to address other issues that are related to what we're doing. And I listened to the two interesting presentations before me. So the presentation here will take on part one and part two, as you see. First, the electric resonators, as you know, is a very important area for antennas in general, and I'll deal with that in detail. But before I do that, I just want to mention, my thanks and thanks to my colleagues at Queen's University. As you can see from the title here, I work at the two universities, so I'll give you a bit of idea about the environment here and so on, and then move on to other aspects. So I also will take this opportunity to talk to you about IEEE activities, and especially for other colleagues and young scholars to benefit from what's happening there. So this is just where I come from, and you can see Kingston there. You all heard about Queen's University in Kingston. So this is where Kingston is located at the bottom of the page, and you can see where we are in Canada. We're somewhere between Toronto, Ottawa, Montreal, most famous places, and you can see the country is here is big enough for 35 million people, but Kingston is a historic place. It was the first national capital of Canada before Ottawa and so on, and there are many institutions in here. And this is a map of where we located, and you can see here, this is the Royal Military College. It is the main college for the Canadian forces, and it has officers, and also it has civilians, the graduate students, and we have visiting professors, and all kinds of programs. You see in the other top of the map here, Queen's University, and this is the other or a bigger university, and it's a historic university. It goes back to 1840, and this is where quite a bit of our work is being done. And you can see from the geography here, the two universities are close by. It's a few kilometers of walking distance, so students go back and forth. And Queens has a very integrated, you're talking about 25,000 or so students. So this is basically the the university that offers everything in there. Now, if I look at this is our university here, the military college, and you can see the officers and so on. But this is in a nice day in summer. Well, that's not always the year round. And Canada, half of the year is covered by snow and so on. So you can see the shape we are in. I will take this opportunity again, as I say, deviate from the concept of energy harvesting to talk about more about the society, the Antennas and Propagation Society, being the vice president now. So I'd like to convey some messages for everybody, and I think this is important, especially important for the young scholars we have. I see that we have 730 or 50 interested registrants here, and just for the statistics, this is about 8% of the total IEEE members around the world. So you actually have a very huge base of interested people, and I think it is very important that the community in India gets involved with IEEE activities and benefit from what opportunities are available. And I'll just take a few minutes here, and I hope you get the idea that what's happening with IEEE, Antennas and Propagation Society. So as you can see, we have administrator officers, and then we have more than 150 active chapters. These chapters, 10 of them are, I believe about 10 are in India now. Some of them have more members than we have all in Canada. So I think it would be good to get involved with the IEEE activities, and the society encouraged that. And I actually mentioned it in our last ADCOM meeting that we should get more involved in that. You have many conferences and so on. So the idea now is to try to integrate these things in something that will serve the community at best. What does IEEE offer? Offer distinguished lectures. It provides chapters with internationally known experts. I have done this many times myself in India. It has education committees, so more opportunities in education. scholarship and other communities site, special interest groups, and I think some of the presenters in this conference, Jawad Siddiqui, and is active member of that, member of geographic activities, and so on, future direction committee. What this all is offer you window on other activities, offer opportunities, scholarships, and so on, funding for activities with the students, especially with the student chapters, and so on. And as we move along, the society is very interested in supporting activities in terms of young professionals. One thing that was also noticed by members, I believe, is in terms of gender. You actually in India have more women engineering than many other countries. So there is quite a support for all of these activities. And I really encourage you all to get involved with these activities and try to benefit from society. And if you go to the society website, you'll see all of these activities listed there, and you can benefit from it. And especially in view of their present situation, the online activities offers opportunities. You can have workshops, you can have other activities online now, and the society will support that. So in summary, I think there is quite a bit of opportunity here, and I wanted to bring your attention all to this thing so we can benefit from that. I will just take a moment here also to talk about research projects. So these are some of the activities we are involved in. And you can see they all deal with applications in antenna application in wireless in other areas. And as you can read through, some of it deal with the application, some of them deal with the fundamentals of electromagnetics. And we have effort going in, as you see in the last topic, wireless power transfer, and one of our speakers will be talking about that, Dr. Chinmoy Saha. I should mention also that the collaboration we had with the groups in India has been very effective, and I'll talk this later in a second. When you're doing research, you got to have collaboration. Collaboration is very beneficial in that. And I hope this workshop will result or initiate quite a number of collaboration activities between ourselves and other institutions, and between some of you together, and so on. So you can see our, we're not a very big university, but we are collaborating with many other places in industry, in other universities in Europe. We have collaboration with universities in India. I see REHS in India, but we have other places in the south and so on. And this has been very, very beneficial mutually to everybody. So I would encourage that activity, across the whole area. Now, I'll talk a bit about antennas here, and I'll take this opportunity to speak in general about antennas as an area of research that is important. As our earlier speaker said, if antenna fails, everything fails. So antennas are important in almost all electromagnetic applications. And to really be innovative in antenna design and come up with a good radiating system, you need to know, obviously, the basics of electromagnetics. You need to know RF and microwaves, and as we have seen for energy harvesting, you have circuits, you have components, you have devices to worry about that. There is the signal processing aspects, especially if you're talking about wireless applications. And then all of this is dependent on one thing, the fabrication aspect. You're going to have a good way of fabricating it to precision, and at the same time making it easier for the industry and so on. That fabrication aspect is very important for all the antennas on design, and especially important for the electrical antennas, as we're going to find out later in my talk. So we're all using antennas, and we're all using phones. And if you look, this is an example of not a very recent iPhone, but you can see here that you have several antennas. This one has at least 6 antennas to cover different bands, as you can see there. And the point here is you're going to have crowding of antennas on all of these devices, and that means you're going to have to face the challenges of all these antennas being accommodated in a small area. All of these antennas are working close by, so there is going to be effects, coupling, all of these aspects. So the point here is that we actually have to go back to the basic fundamentals of antennas and understand more about antennas in the near field, more about antennas in the far field, how they affect each other, and so on. That suggests that we actually have quite a bit of research ahead of us in looking at these things. And these are some of the aspects that we're actually dealing with here and many other labs around, and we're doing collaboration with quite a number of groups on that. Antennas on a plane. You fly in a plane, and this is an old plane, and you can see the number of antennas on there, and for various applications, and they go from very low frequency to very high frequency. Some of them you don't see, some of them are conformers, some of them in different spots. And if you just look at the range of frequencies that you see these antennas working at, you can see that they're going from the low kilohertz all the way to the high gigahertz. And things are not going to get any simpler. There's going to be more antennas, there's going to be more requirements, and so on, especially with the way things are going. And if you look, and this is an example of what antennas could be on a car for radars, for monitoring things, for GPS, for various aspects of communication. And if you look at the title here, this title actually is quite true. They are our eyes and ears, and if we're doing energy harvesting, they are more than eyes and ears. They collect the energy and so on. So this is an important aspect that there is going to be quite a bit of research on it, and we're going to all face the challenges of designing these antennas, accommodating them, and so on. So that would suggest us to look back and see what is it that we need to do, and how the new and young researchers would like to align their way ahead. And this is all my suggestion based on what I see around, and it's by no means exclusive and so on, but I'm looking at the way things are going. And if you look at what advances we see in antenna research, well, you're talking about 5G, we're talking about CubeSat, we heard some information about that. Internet of Things, smart homes, and all of these things. So, well, what does this entail us to, or what does this present in terms of challenges to us? let's have a bit more information here. What is the Internet of Things? It's a new, application, and you can see where all of this automotive, healthcare, home, smart cities, environmental. So basically, as it says here, antennas are being used almost everywhere, business, industry, and so on. So what does this mean? Well, if you look at some of the information I gathered for the just the benefit of knowing what's going to be happening, you can see how many devices will be there, total data created, its effect on the economy, and so on. And I'm gathering this information from the communication and business journals. If you look at the Internet of Things, for example, with the interaction of many devices uniquely identified, they do sensing, they gather and receive data and communicate with each other. So all of this is going to be done, and antennas are going to play an important role in that. So what is it really that makes an IoT system, Internet of Things system? You have objects, and you have networks, and then you're going to do the computing and intelligence and so on. If you look at a logical data cycle, you're looking at acquisition, analysis, aggregate, acquiring that, transportation. All of these things are going to play a role in they already are being implemented in one way or the other. And here is an example of we looking at this example, for example, in a hospital situation. Well, that I guess is going to be more relevant now with the COVID and what's happening. But if you look at a patient room, you have sensing, you have sensors, you have data. Then you go to the monitoring the patient. You can have up to 50 sensors, and you go into from there to the central place to electronics. So it is quite an involving thing in there, and you're looking at lots of centers and RFIDs and for reliable network infrastructure. You're talking about 5G, global navigation satellite system, GPS. All of these aspects. And if we look at how things evolved over the years, you can see how wireless phones were there, and you're looking at the development from 1981 to how it developed over the year until now, and the data requirements and so on. So we go from 2 kilobits to 10 gigabits. So it is quite developing as well, and people talking now about 6G and so on. Same thing as you said earlier, type of the data, type of the uses, and involvement. These data you can find in any of the communication journals, and people talking about massive MIMOs, multiple input, multiple out antennas. So these are the direction things are going, and that would involve designing of these systems, looking at the properties there, how to design them in the environment, how to implement them, what kind of interaction, and so on. And if you look at some of the challenges, like if you look at an antenna like this, which is a small at 3.5 gigahertz. If you go up to higher frequency, you can see the challenges in the design and how it goes from one size to the other. So that's another challenge in the fabrications. And as we go up to higher frequencies, same thing. And these are some of the antennas that people are talking about for 5G. And you can see there are various designs, there are various trials. If you look at the new development, if you look at the conference in Montreal, or was supposed to be in Montreal last week, you can see the number of papers, the MIMOs, people now talking about bridging the gap between electromagnetics and the communications, as we're trying to do it here also with energy harvesting and so on. So, you know, the same thing with communications with GNSS, Global Navigation Satellite Systems, various frequency bands, and how the systems work and so on. So, this is basically why we have to look at what specific challenges lie ahead for us. And these are some of the areas that I thought I should bring up to your attention. So besides what we're doing for antennas for energy harvesting, we can think along, and those of you who are working in different areas can look at these things and identify some research problems as we go along. So basically, if I look at the first topic I have here, which is advancing the analytical techniques in electromagnetic research. Well, if you look at the history of electromagnetic research, until the 80s or 90s, before computational method, there was focus on analytical techniques and the fundamentals. That kind of seems to have faded away a bit with computation. But now, as we come into the crowning of antennas, and many antennas close by, as I showed in the previous examples and so on, we see that it is time to go back to the fundamentals and try to understand how antennas interact with each other. When you design them on a chip, or you're working sometimes in the near field of antennas. And the question comes is, how much do we know about the near field of antennas? We actually fire antennas and go to the far field, but as far as the near field, we don't know too much. So this is one area we worked on. And when you're crowding this, you have sensors, you have many antennas together. Antennas are actually interacting with each other in the near field. And we make assumptions about them being in the far field, or use far fields concept to deal with this. And this actually gives us issues in some of the design application, especially in MIMO antennas, where actually mutual coupling becomes an issue there. And you can't analyze mutual coupling based on far field or circuit parameters as being done now. So these are some of the concepts that we need to look at for the other applications. Another important area that's coming, and it's going to be with us for a while, is basically electrically small antennas. Whether we are looking for application for energy harvesting or other applications, this is a challenge. And a challenge because when you make the antenna small, other problems come in, like matching the antenna. Antenna small, they have small impedance. How you gonna make them? How you gonna match them? And as was said earlier in the first talk, matching antenna is important. So this is one challenge we have to be there. We have to deal with. New fabrication techniques. Well, that applies to what the issue we have at this stage, which is the electric resonant antennas. You're going to have to find new ways to do them. New materials for antennas, polymers, advanced dielectrics. We now see antennas on wearable antennas that are small, that can be embedded in the body. Then, and then when you can't achieve with one antenna, you need to have combination of antennas. So the question about antenna arrays and so on. How you design these arrays for whatever application you have, whether it is communications or other applications. We heard this morning about need of wideband antennas for energy harvesting and so on, and for GNSS application. Wireless part transfer. I think we're going to have a talk about that, and this is another significant area of research that's coming. And then the topic of the day, antennas for energy harvesting. Are we going to be using the type of antennas we have now, or are we going to be designing antennas that are more efficient and so on? So these are some of the topics that we look at that. So having said that about antennas, I hope you harvest something from my talk about the importance of antennas and the challenges that lie ahead for us. And as I said earlier, there's quite a bit of opportunities of collaboration, knowing what's happening. Young researchers and scholars, I think you need to get involved with the community. You need to get involved with the AP society and benefit from the various aspects there. And with technology now, you have everything at your disposal to do what is required to achieve real advances in the area. So generally, if I have, as Timur said, I have been working. He made me look very ancient, which is all right. But if I look back and I think some of the most important challenges are still lying ahead of us. Or as somebody said, all the easy problems have been solved. Okay. So having tried to give you that idea about what lies ahead, I'll focus now on the dielectric resonator antenna, the topic that I'll be talking about for a while here, depending on how much time we have. I don't know, Timur, how much time do I have left here? Hello, you hear me? Hello. Am I still audible or Timur?
Yes, sir, you are audible.
I'm still audible or
15-20 minutes you can take. 15-20 minutes you can take as per your convenience.
Okay, I'll take 15 more minutes and then.
Yes, no problem.
Okay,
because
so
your lecture is divided into two parts. As per your convenience, you can conclude, sir.
15-20 minutes you can take. 15, okay, I'll take 15 more minutes and then I'll stop.
Yeah, sure.
So what is the dielectric resonant antennas? Well, just for those who are new to the field, this is something that started in the early 80s and it has gone quite a long way since then. And it is interesting area for research, interesting area for application. And what I will try to do here is give you a bit of a general overview of what is there, and at the same time try to indicate some of the challenges that lies ahead. And so it is an area that that's very, very interesting in terms of application and so on. It offers new opportunities as long as we can face the challenges that are in there. So the electrics have been used in microwave circuits for a long time, and they are being used as storage devices. And there always have been interesting research, their properties and so on. It goes back to long time, as you can see, from the theoretical research, and then the and the properties of the electrics and so on, and then when they used as not an antennas but as the electric resonators in circuits, as you can see from 1939 and on. Then they were used mainly in filters and so on, and these are some of the milestones that you can see in there. And quite a bit of work exists there, and just to give you some idea about like as I say, it is a resonator. It's a high dielectric constant, so you can actually sandwich the fields inside the resonator in various types of modes. And if you look at this equation here, basically, if this is the reflection coefficient here, if you have high epsilon r, then that reflection coefficient, this is high epsilon, so that gamma gets close to 1. So you basically have like a totally reflecting surface. So this means you can actually store the energy inside some of these resonators. How you store the energy there and how you make use of it and so on. So you can store the energy, you can store the fields there, and then that could be as a resonator. But if some of the energy leaks out, then you have radiation, and this was the basic idea that started. So what is the first, there were some effort before about using resonators, but they really didn't call it antennas at that time. And though there was some radiation, it was Stuart Long at University of Texas in Houston that first produced that paper about antenna, the electric resonator antennas. And then after that, there was a flood of work that went along with these things, and we got involved in that actually in the early 80s as well ourselves, or late 80s. And at that time, there was only a couple of universities, Houston and Mississippi, and we got involved in there, then CRC in Ottawa, and then all of a sudden now you find about 40, 50 universities around the world are doing research on that. So what the basic idea, as I said, you store the energy in the resonator, then energy leaks, and if energy leaks from the resonator, then you can have yourself an antenna. And the question is, can you control this leakage to achieve the properties you want to have in terms of antennas, in terms of radiation pattern and bandwidth requirements and so on? What you see here is some of the shapes of the electric resonators. As you can see, they take on various shapes and I'll go through some of those as we go along in our talk. Some of the recent literature, if somebody wants to learn about these antennas, you can see the number of papers and so on that are there, but the first really reference on that was this book to the left here, which was edited by our colleagues at Hong Kong, and it gives some of the early work. And a very good reference, which is written a few years ago, but still actually very relevant, is a book written by Aldo Batosa, at my colleague at CRC. I've done quite a bit of work with him. And then the antenna handbook has a chapter, even the updated one has a chapter on that I was involved in. And then of course, with all of that, you need to know about the properties of dielectrics and so on. And this is, your own Professor Sebastian. He actually wrote quite a bit. He worked quite a bit of, did quite a bit of work on properties of dielectrics and so on. So there are other couple of books that appeared recently, and so the literature is quite rich now on these things. Why use this? What are kind of advantages they offer? And I think some of this is relative to what we're doing here with energy harvesting. And you can see the first thing is low dissipation loss, using a very high epsilon and very low segment. So the material is low loss dissipation. So it basically have a high radiation efficiency. And we're talking here, if you tune the antenna right, or the resonator right, and so on, you can have actually efficiency of about 98%, which is quite a bit higher than what you could achieve with microstrip antennas and so on, because you have very little in terms of ohmic loss. It has low radiation Q factor, or at least the modes that radiate have a low Q factor, and that will give you wide bandwidth. When I'm talking here about wide bandwidth, you can actually achieve simply 50% and sometimes higher than 100% bandwidth with these type of things. Wide frequency range of operation. Well, you have seen some that goes from 55 megahertz to 135, and probably now this information is a couple of years old, but there could be higher than that. The 50 megahertz I'm referring to is actually some work in the UK where they use water as a dielectric. Okay, so that is some interesting application. No service waves, low mutual coupling, no scan blind, wider scanning range. Well, these are all important properties for antennas, and as you know, service waves, when you do planar circuits and microstrip antennas and other type of printed antennas, you can see that service waves is a double there. So this is something you don't see in the electro-radiation antennas, provided you do the feeding right. Design flexibility. Well, you saw the shapes over there. These various shapes are a way of achieving center properties, certain modes, and so on. So you have actually design flexibility in there. Well, that second one, or that one there about easy integration with other devices, I'm not sure this holds all the time, but you can integrate them with other devices. Different radiation characteristics. From the same antenna, you can actually achieve various radiation characteristics, because you can actually, within the same resonator, you can excite certain dielectric modes that give you certain radiation characteristics. Well, mechanical simplicity, this is obvious, and then less susceptible to tolerance errors. When you're doing a microstrip antenna, you basically have to be within certain tolerance. With the dielectric resonators, these are a bit more relaxed. Well, they can have higher power capability because there is no breakdown in there, and then wide temperature range. Well, that doesn't mean that they don't have disadvantages, and some of the disadvantages are that you can see here some aspects of it until now are still unknown or unexplored. Theoretical analysis until recently are still not fully well developed. Most of the work that you see or we have seen is based basically on numerical simulation. Obviously, they take a volume, so they are not as low profile as microstrip antennas. The fourth point here, fabrication can be challenging, and I think this is a very important thing, because you can use blocks. The cutting and doing this to precision is not easy. There is ways now of doing it using different fabrication technique in terms of depositing the electric and so on. And this is where some of the challenging fabrications and integration would be interesting. Sometimes integration with circuits is a challenge, and we had some of that when we were trying to do it on antennas on a chip and so on, in terms of the circuit properties there and so on. And you need advanced challenges for them. Well, some of the working definitions and properties I see here. The various shapes, the rhythm frequency can be a function of size, shape, and the material properties. We're talking here about materials that epsilon that could go from anywhere from high epsilon. We have had some that were designed as using epsilon of 6, and you see some design that go epsilon to higher values, 20, 30. The higher you go, there is limitations on the bandwidth and so on. But basically, the dimensions of the RE are in the order of lambda over square root of epsilon, lambda in the dielectric. So basically, there is a bit of a size reduction there for the same frequency. The one advantage, as I said earlier, it can be designed designed to work for number of modes. But these modes, like not all the modes in the dielectric resonator radiate. So these modes, you have to be very selective about your choice and so on. The same thing obviously would apply when you using them for energy harvesting and so on, because some of the modes will behave differently. They are mounted on a ground plane normally, and that would have effect on their properties and so on. Method of analysis, as I said, for some of them there is very accurate numerical, accurate analytical techniques, as you see in the top there, and especially for the spherical shapes where you can solve the boundary value problem easily. There are some approximate analytical techniques using cavity model of the electric waveguide model, but most of the analysis are using using numerical techniques so far. The resonance modes and so on. Maybe I should. It's a good time to stop here, and we can deal with that issue later on. So if you allow me, Daimur, I think I used my 15 minutes. I'm fighting now with dinner time for you in India, and I'm not sure anybody harvest too much from my talk after now. So I'll stop right here.
Thank you, sir. Thank you very much.
Yeah.
Thank you very much, sir, for this quite informative last lecture of the day. We have several new things, several new challenging areas. We have learned where we can explore ourselves, our skills for developing new kinds of antenna. And with this one, I think I'm not observing any quite relevant query from audience side. All are some general queries which can be handled easily. Okay.
Well, I'd like to add, if anybody has any questions or any requests for information about this topic or about what AP Society offers for people in terms of workshops, in terms of conferences and so on, please feel free to make use of me in the new job that will be lasting for a year. Thank you.
Sure, sir. Sure. We will try to that. Thank you, sir. Thank you very much once again for sparing your valuable times. And I am continuously observing since the moment when I logged in the starting of the workshop, and continuously I am seeing your energy and your enthusiasm since last more than 4 hours.
Oh, thank you. I really enjoyed the participation as much as.
I think with your kind blessings, the remaining 4 days will also be quite informative for all the participants, for all of us, as we have planned to learn something new in the days to come. And finally, we'll meet you again on the last day, that is second part of your lecture. And in continuation of your lecture, I think Professor Chinmoy Shah will be continuing tomorrow in the first lecture as per our schedule and as per our discussion.
Yes, Dr. Khan. Yeah. I'll be continuing from here, and I'll talk about that.
Okay. Thank you with this one. Thank you all who are okay. What is that? Sir, now one query is there from one participant: how to calculate conductivity of a dielectric resonator antenna?
How to calculate it?
How to calculate conductivity of a dielectric resonator antenna?
You actually, you cannot calculate it. It comes with the material, so you actually have to know the properties of the material. So it's a material issue. It's not, and you're gonna have to trust what the manufacturer said. But you basically, if you are looking for very precise things, you can actually do measurements using waveguide techniques to measure the dielectric constant of the material. But you cannot calculate it unless you're a material scientist and want to go into more things, which I'm not really aware of, any way of doing calculations as such. But as I say, you take the value, and most of the time is not very precise. So if a situation requires, you actually have to do measurements, and there are microwave measurements techniques to measure the dielectric constant of the material, including the losses. Yeah.
Okay. Sir, another query is which material is preferred for DRA, FR4 or some other material, dielectric material?
I'm sorry, I didn't get the question. Which material?
Yes. One participant has entered a query: which material we will use for DRA, which dielectric material, or it will depend on some applications to application, or varies from application to application.
Yes, it depends on the application. It also depends on the requirements, and you can have material that from epsilon, as I said, from 6 up till higher epsilon, up till 60. But the problem is, like dielectrics, you could have a dielectric constant of very high value, but once it is high value, it is actually not good for being used as an antenna, because the higher dielectric means the energy is contained or stored in the dielectric and doesn't leak out. So most of the designs would go from, say, 6 to 30, epsilon 6 to 30. Okay. So the material and properties have to be within that range. There are new ways of depositing material using and so on, and I think we'll talk about this in the next little while. Okay. But if you're asking me the question, where would I get the material? I think I'll just go to a place where they make them, or look at the literature on dielectrics as such. The book by Professor Sebastian and so on would be a good source of that.
I think what reference books you have highlighted in your presentation, that will be sufficient for that query.
Yeah.
Okay. Sir, the last query from audience side is, what about permeability of dielectric resonator?
Well, it's one.
Okay.
And there's like it's not a ferromagnetic material. Yeah.
Okay.
I haven't seen an application yet which combines both material that has both, but maybe other speakers will have experience and talk about that.
Yes, sir. Sure. Okay, sir. Thank you very much.
I see nobody wanted to ask about the AP Society and the activities, but that could come later, as I'll be willing to answer any question.
From my side, it will be discussed later on, because in the continuation of this session, I'm not able to understand what type of discussion should be made here. Later on, I think in last lecture or some other time slots, I'll discuss that one.
Or maybe I can raise that more into my last day of lecture.
Yes, sure.
Yeah, I see Chinmoy, you have
Sir,
a question?
Can I
Chinmoy,
propose
or a
rather small panel discussion?
Yes,
no,
please.
No question. I am just suggesting, in connection with Dr. Khan's comment regarding the AP activities and the type of things that we can leverage from IEEE APS. Maybe we can have a small panel discussion kind of thing where Professor Anthar will be the lead speaker, and we can ask our queries and kind of
stuff,
so that we can have the full benefit of IEEE APS.
Sure. Recently we got an approval of IEEE MTT student chapter here. For the formal inauguration of that one, we can arrange a 1-day, 2-day event later on after this workshop, as per your convenience, Dr. Chinmay Shah and Professor Anthar.
Okay, that's wonderful. That's wonderful news to hear. Yeah, so
yes, sir.
There will be opportunities that we can explore with that. Yeah.
Yes, sir. Later on, we can think about how to create the interest in youngsters to be the IEEE members, or IEEE, how they will contribute to IEEE society, or how they will get benefited from IEEE also.
Yeah, and it's really a good opportunity if we have that huge number of participants. So
yes,
the